Guys, sick, guys. Yes, Miko. That was a Miko. Yes, Michael. Yeah, that's a violation, bro. My bad. I'm actually so tired. I don't even know why I'm tired today. Yes, yo. Uh, was paper two not good? Mikhail. Alright, Mikhail. Was paper two not good, guys? Like, to be fair, I heard it was mixed. I heard there was lots of polymers. You know what? Today's paper three maths. The guys that were doing maths, I respect. Guys, he's tired, bro. They're tired. I get that. Guys, one exam left and it's over, bro. Oh no, it's just over. It's actually bugging. I don't know why it's bugging. You're gonna have to give me a sec, but I'm trying to figure this out. Yeah. Oh, there we go. Okay. My camera's looking a bit unsaturated. Why is that happening? I need to get a new one, bro. I'm not a fan of it. There we go. I don't look orange though. Yeah, it just feels different to me. Maybe it's just extra bright outside, that's why. It's a hot day. Alright, oh. I sound like an alien. You know what? Wait. How about now? Because I have a fan on. Does it sound better? Yeah? No? Sounds ass. Does it sound good or no? I just turned my fan off now. Is it good? It's my fan. Wait. Okay, wait. Let me move my fan here. Look. How about now? Is that still calm? Or does it still sound dodgy? So I can't survive without this fan, bro. It's gonna be mostly exam questions today, I think. We're gonna focus on chromatography. Alright, cool guys. We're gonna focus on chromatography, pH curves. We're gonna look at the iodine clock test. Let me see what else. Let me get my PowerPoint up actually. I made one yesterday. Yeah. Yes, MK, yes. A mix of, yeah. So we've got KP stuff, heterogeneous catalyst script. I'm gonna look at electrodes a bit more, just because I think it's just gonna pop up in multiple choice. I think it also pops up in multiple choice. DNA, Cisplatin a bit, gas chromatography, column chromatography, and normal chromatography. Bit of mechanisms that you haven't seen before. So like, yeah, dehydration, hydration mechanism, EZ isomers, and pH curves. I think I already said that, and essentially just some multiple choice questions. Yeah. Love you too, Dean Center, man. Love you too. Good question, UB. I'm gonna make it around maybe 2.5, maybe 3 hours. But yeah. All right. What do you mean take your money, bro? Don't. To be fair, I added a link. I added a link in the description if you really want to give it, bro. But you don't have to, man. You don't have to, bro. You don't have to. What practicals? Good question. Iodine one. I'm gonna focus on. I think this one is going to be. I believe this is very similar to the iodine one. I mean, EZ isomerism can come up in any way. That's the thing. It's like it's just one of those things. In multiple choice, anything can pop up. Time of flight. I might go over time of flight a bit, but to be honest, I don't think it's going to be a big, it's not going to be a chunky question. Reflux, potentially, they might just ask you to draw the diagram. That's, I think, kind of a limit. Guys on TikTok, if you want to come to YouTube, man. You know what, let's start. Thermodynamics, I don't think it's going to pop up. Like, there's not going to be a bone harbour. I think there's going to be disappearing cross, yes, there are. I think there's going to be disappearing cross or iodine test. I think thermodynamics, if it pops up, it's going to be coming up in multiple choice. BMZ, I think, is going to come up in multiple choice. It's going to be like, how do we work out the mass of one atom of I don't know, chlorine or bromine or anything like that. Alright, it's maybe 3 hours. So maybe finishing around 7:30. Alright, you know what, let's get started. Alright, this it's not like a whole paper essentially. I kinda wanna go through a bit of it just because this looked really interesting to me. But I wanna kind of go through this and then all of this multiple choice potentially, maybe not all, maybe skip through a bit. I kind of want to show you the exam technique of how you should approach multiple choice. You might have already practiced this paper already, which is fine, I guess. But yeah, let's do this. Yeah, you didn't have to, bro. You didn't have to do anything. Alright, let's look at 2021. 1 second, guys. Okay, we got hydrogen peroxide. Oh, I really appreciate that, my bro. Thank you, man. Calorimetry, potentially. Okay. Hydrogen peroxide solution. Peroxide solution decomposes to form water and oxygen, and the reaction is catalyzed by manganese oxide. Okay. A student determines the order of this reaction with respect to hydrogen peroxide. The student uses a continuous monitoring method in the experiment. The student places hydrogen peroxide solution in a conical flask with the catalyst and uses a gas syringe to collect the oxygen formed. The student records the volume of oxygen every 10 seconds for 100 seconds. Why is the rate of reactions the highest at the beginning? Good question. Well, when you have the rate at the highest at the beginning, essentially you have the most amount of reactants at the beginning. Meaning, if there's the most amount of reactants, you're gonna have more particle collision between your reactants and your reactants. Really, both of them are your reactants. Yeah. Let me see what you guys are saying. Good. Yes, I like that. I like that answer. That's probably going to give you full marks there, BMZ. Okay, so you have highest concentration of reactants, and therefore more successful collisions. Okay, I would recommend try to think about where is your marking points coming from. Okay, you have 2 marks. What 2 marks are you kind of making? Yes, amazing, Tilly. Perfect. Full marks for that as well. Okay, more successful collisions. I put successful twice. There we go. Yeah, I'm actually very tired today, so please bear in mind. Can I zoom in? No. Come on TikTok. I mean, come on YouTube from TikTok. Do you need to know the methods inside out? I'm gonna say no, just because the way that chemistry A level is for AQA anyways, and I'd argue even for OCR, it's essentially they give you it in a different context, and essentially, yeah, I changed my mind, Sid. I changed my mind. And I wasn't doing paper 3 for maths, but essentially, the way that practicals work in AQA is that they take it and then they apply it on a different context. Like for example here, this is to do with your order and your rates of reactions. Normally that's going to be to do with your iodine test, but in this case it's not. In this case you're working with hydrogen peroxide. Okay, and sometimes it's not even like, this is still practical skills. This still comes under practical skills, even though it's not a practical that we've necessarily learnt. Okay, this one I'm just going to quickly go over. Draw a tangent to the curve with the concentration of hydrogen peroxide solution is 0.05. Well, 0.05 is here, and if I zoom in, what I'm gonna do is draw a straight line to 0.05, and then essentially at this point you're trying to draw a straight line where the gradient is almost the same at that point. Okay, that's probably the best tangent I can get. Oops. Okay, and now it's saying calculate the gradient of the curve at this point. Well, what you can do is go ahead and make a right angle triangle. Try to make a right angle triangle where you intersect at kind of squares. So I'll probably say here and here. Like by the squares I mean like these little grid bits here. Okay. No, Asian, no. Don't need to. Okay. I'll show you. I've got a question for that actually. I believe I have it here. I really want to look at that. Is I think from 2021, and I think it's a really good mark scheme to just honestly learn. Just trying to see where it is. Yeah, I've got it. Okay. Anyways, working on gradient is pretty simple. You find your change in y, divided by your change in x, or in this case your change in y is going to be, this is 0.62646668, so this point up here is going to be 0.068, this one's going to be 0.028, that means your change in y is going to be equal to 0.04, if my maths is good. The reason why sodium thiosulfate, it's not really necessarily about the sodium thiosulfate, it's about the fact that it's a starch, okay? Because with the iodine test, is that it turns into dark blue, and the reason why that happens is because you're essentially testing for starch, right? The sodium thiosulfate, I guess, is to do with your rate of reaction rate. It doesn't really matter what you use. You can use any. Oh, I don't want to say anything, but essentially anything, depending on the context of the question. Okay, but the reason why it actually turns black is because of your iodine test. Anyways, your change of x here, well, this is going to be 2, 4, 6, 8, 10, so that's going to be 4, and then this one's going to be 22. Change in y, change in x, sorry, is 18, and then that's going to be essentially your rate. Okay, sometimes they do ask the units for this, and always just think about, well, what's your units on the y-axis? Well, the units on the y-axis is moles per decimeter cubed, and then your units on the x-axis is just time. So that means your units is going to be moles per decimeters cubed per second. Okay, and whatever that answer is, if I put that into my calculator, it should probably get into my screen. 32. Thank you. Thank you, Bryn. 32 moles per decimeter cubed. All right. Cool. Let me get my calculator on screen as well. So yeah. All right. Let's continue on. Now this looks really, really complicated. Okay, but they've given us a. I put 22. Not 32. Oh, sorry. Oh yeah, you're right. Yeah, you are right. So that becomes 28 on the denominator. Sorry about that. Yep. You're right. So 0.04 divided by 28. That gives you 1.429 times 10 to the minus 3, which is still fine. I mean, cool. 1.429 times 10 to the minus 3 moles per decimeter cubed. I think they will as well. I think they will, Sid. That's why stay on top of your time of flight, but don't necessarily prioritize it. And actually, you know what? I'm gonna skip past a lot of this, and instead, what I'm gonna do is actually, I'm gonna, you know what? Screw this. 1 second. I'm gonna change your plans. Change your plans, guys. Autocatalyst stuff. Okay, I think autocatalyst stuff is gonna come up. Yes, sorry. Yes. Kind of, yes. Chromatography classes as a practical, by the way. Chromatography is a big practical. Your iodine test is your practical, and there's a specific heat capacity that is your practical as well. I will go over the specific heat capacity stuff. All right. First of all, autocatalyst stuff. Let me get actually my notes for this, because I have notes for this. But essentially, what the definition of an autocatalyst is that a reaction produces its own catalyst. Okay, this is going to be it's going to produce its own catalyst, and that just means that as time goes on, your reaction gets faster. And usually, where you'll see this is specifically with your manganate ions producing Mn2+. Okay, I don't think you've seen this yet in paper 1 or paper 2. Do I think will I think that it can pop up? Actually, you have seen it. You have. I've looked at one of the unofficial mark schemes, and you've kind of briefly seen it anyways. I think the definition of it will pop up. I don't think the equations of it will pop up. But just in case, I will give you guys the equations that you can memorize. Not contact process. No. This one's with autocatalyst stuff. 1 second, guys. So there are essentially three equations, technically 2 equations you need to know. Again, this is inorganic stuff that you just kind of cram in. Yeah. Okay. So this is probably one of the equations. If you guys got it right or seen it in the unofficial mark schemes, you've probably seen this equation. So the overall equation normally is going to be 2MnO4 minus plus 16H plus. Actually, you know what? Don't even learn that. Instead, what you should learn is learn this. Okay, start by learning this and then do your half equations with this. But you also need to remember that there needs to be some C2O4 ions. This might pop up. I'm going to put this like as a 30% chance that it'll pop up. Okay, but I'm going to give it to you guys anyways. Okay, so this C2O4 minus goes ahead and reacts with MnO4 minus as well. But remember, we need a catalyst with this, and that's going to be essentially a catalyst is Mn2 plus, and I'll show you how that goes ahead and reacts. Okay, if we have a essentially this is an ethane diowate ion. What is produced is carbon dioxide. Okay, and what we're also going to do now is balance this using redox equations. Well, at the moment we have 4. I'm just trying to think how we can balance this without make it. I'm trying to make it as easy as possible to memorize. You know what, guys? I'm just gonna put it on screen. If you want to memorize it, you can. If you don't want to, it's not that deep. Okay, these are the exact numbers. If it pops up, pops up. If it doesn't, it's only 1 mark. Okay. I'm not gonna fuss over this too much because I want to make this as easy as possible for you guys. And to be honest, it's a low priority, a low % chance that it'll pop up. I'm not gonna fuss about it too much. Okay, that's one of your equations. This is another half equation that can pop up. This is going to be with your Mn2 plus, which can go to 5Mn3 plus and 4H2O. If you want to cram it before your exam, cool. And this is the equation that came up in, I believe, paper 1. I think this is the equation that came up. I've seen this in one of the unofficial mark schemes, and because this came up, I think it's unlikely that autocatalyst equations will come up, but there's still a chance that the definition can still come up. I'm using a graphical tablet. Right now I'm on Autocatalysts. But moving on, I want to start to look at some pH curves. So pH curves, I actually see a decent amount in multiple choice questions. Okay, and this is some stuff that they can actually ask you. And I used to get this type of question wrong all the time, but I don't think it's that bad. So essentially, what they'll ask you is what, and they might give you like a table, but what indicator is best for when, for example, HCl is added to ammonia, let's say. Okay, now this is a pH curves topic, and they'll usually give you a table to help you indicate you have a pH curve. Potentially, yeah, in a multiple choice. If they didn't ask you about indicators in paper 1, did you? Did you get something about indicators? I'll go over this anyways, okay? Because that doesn't mean that it can't come up. Okay, and then after this we'll look at some DNA stuff. Actually, I should probably follow my list that we have. I'm gonna go over KP. Let's do KP after this. Oh, we got no, we got yes. Yes, did it come up? And let me show you guys anyways how to go about this. All right. Well, start by drawing yourself a pH grid and just label it from 1 to 14. 7, 8, 9, 10. Can we end up with paper 1? Fair enough. 11, 12, 13, 14. Well, we know, let's start with it's a multiple choice. Was it actually? It probably won't then. Probably won't come up then if it's a multiple choice. Okay. But ammonia is a weak base. HCl is a strong acid. You need to be able to determine which is a strong acid and which is a strong base, weak base, and such. Okay, weak bases, they're generally going to be around 10 to 11 pH. Okay, nothing less than 10. Do never ever put 9. 10 is the lowest you should go. Strong acid is between 0 and even 1. I wouldn't push 2. For weak acids, if you want to make a note of this is around 2 to 3. 4 is pushing around buffer region. Okay, and then obviously strong bases, these are around 13 or 14. Okay, take a note of this because if they ever ask you about pHs and such, also the pH of magnesium hydroxide is around 10/11. Okay, magnesium hydroxide is really high on your periodic table, but because it's insoluble and it's not fully, I should say, barely soluble, I should say. Essentially what happens is your hydroxide ions can't be released very easily, and that means it's essentially a weak base. Okay, they don't really like using it as a base, and if they ever ask you about what's the pH of magnesium hydroxide, just put 10. even put 11. You probably get away with 11. 10 is a safe number though. Okay. Anyways, let's continue with the actual question itself. When HCl is added to ammonia, let's start with ammonia. But usually they'll probably tell you what to start with. Because we're adding HCl to ammonia, we're going to start with ammonia. So that's going to be around pH 10. HCl we're going to finish off with around pH 1. So your weak acids, MK, your weak acids are your carboxylic acids. So if you ever see a COOH, ethanoic acid, butanoic acid, those are all your weak acids. Okay, ammonia, benzene, any phenylamines, that sort of stuff is your weak bases. And then your sodium hydroxides, potassium hydroxides, those are your strong bases. Okay, now when we have a strong acid, the thing with the strong acid is you're going to make a very, very steep peak. But when you have a weak base, okay, you're going to make a shallow kind of, almost a shallow transition. Okay, it's not a steep transition, not like that, but also needs to be like kind of gradual. I should probably move this a bit more back. You can see that it's not really matching at the moment. And you can obviously do this in pencil. Okay, and that's going to essentially be a graph. Okay, now obviously when you do this in the exam, you're going to make it a bit more nicer than me. Okay, and you're going to be trying to make yourself a vertical region. Okay, and the vertical region here will be anything that's outside the curve, which is 8 and probably around 3.5. Okay, now they'll give you some stuff. Okay, they will give you some pHs, or sorry, indicators, where there are maybe 2 or 3 I'll say most likely 2 indicators that fit. Okay, and you might have seen these type of questions and maybe some past papers from multiple choices. Okay, so there'll be some in, let's say, phenolphthalein. Phthalein is, let's say, 2 to 7. These are some made up numbers, by the way. Okay, let's say methyl orange is, I don't know, 4 to 6, and then methyl blue is 5 to 7. Okay, well, you can see at the moment, out of these 3 indicators, 2 of them fit. Okay, this one does not, but 2 of them fit. But this will be a multiple choice question. So how do you figure out which is the actual right answer? You want to pick the one that is the most comfortable within this region. Okay, so 4 to 6 is really, really close to your 3.5. Okay, so 4 to 6 is probably around here and here. Oh, 3 to 6 is there. Whereas 5 to 7 is here and here. The more comfortable region is your 5 to 7. So the correct answer in terms of your multiple choice, you would pick methyl blue, not methyl orange. Does that make sense? Okay, I used to get these questions wrong and I couldn't actually figure out the actual reason until I thought about it more. My teacher didn't really give me a proper answer, but that's the best reason I can kind of come up with in terms of getting it right every single time. Pick the one that's the most comfortable within the region. Okay. Is it not the one with the shortest range? Essentially, yes. Asian, yes. Essentially. So if you the reason why it's the shortest range, it means that it's more comfortable. Okay, it fits within this region. Okay, but 4 to 6 and 5 to 7, they both have, if they both have the same kind of ranges, just pick the one that fits between the two. Okay. All right. Let's look at some KP stuff. Specifically, I want to look at some hard KP stuff to do with algebra. And this question, I can't remember where it's from. Maybe it's from 2020 or 2022. I can imagine this coming up because I think a lot of people don't do well on this type of stuff because it has algebra. Okay, let's start with question 1, 6.1. I want you guys to have a read of this. And if you want to attempt 6.2 as well, I'll give you guys a quick minute and then we'll start. pH curves you can still apply in OCRA, by the way. pH curves you can apply in OCR. However, I know for OCR multiple choice doesn't come up for paper 3. So it'll still be useful though. Okay. Guys on TikTok, if you want to come to YouTube, hop over. The volume question. For what? I think, was there a PVNRT? I wish I had the papers, bro. I genuinely wish I had the papers. Good question, S. What is sodium thiosulfate? Essentially, it's yeah, you're not fair. Everyone's tired after paper 2. Essentially, it's used for your disappearing cross experiment. Okay, so what you have essentially in your while you guys are doing this, I'll kind of talk in the background. With your disappearing cross experiment, you have a bunch of reactants, and your main reactant to do with it is your sodium thiosulfate. Let me actually double check this before I'm waffling. And it's hydrochloric acid, right? Yeah, it is. Yeah. So you have hydrochloric acid, Let me just draw the actual molecule. I think it's NaSO3 thiosulfate, or maybe it might be something else. But essentially, you go ahead and react this with hydrochloric acid, and what happens is it releases sulfur. Now, sulfur is a solid. Sulfur is a precipitate, and it should be actually S2O3. And when it releases sulfur, one sec, Na2S2O3. When it releases sulfur, since sulfur is a precipitate, essentially what you're checking is how fast does the sulfur appear so that the cross on the bottom underneath this conical flask can't be seen anymore. That's your disappearing cross experiment. It doesn't have to be limited to sodium thiosulfate. I can imagine it can probably end up with some iodine and maybe starch. That's still some sort of precipitate that's forming. Okay, maybe, or you just can't see it. That's still your rate. Okay, any sort of precipitate, maybe silver mirror potentially. That's probably a bit of a stretch. Maybe some halide test. It could potentially, I can see that actually happening. Halide tests mixed with your disappearing cross experiment, because one is a halide test, and two, you can't see the cross anymore because precipitates are formed. Okay, that's essentially the main purpose of it. Does not only release sulfur with iodine. Not necessarily, Emmer. No. So as long as, because sodium thiosulfate is a base, right? And you react it with hydrochloric acid, what you'll make is your salt. You'll make sulfur. You'll make sulfur dioxide, and potentially water, because it's just a neutralization reaction. Okay, and obviously that's not balanced, but yeah. Yeah, you're the bromine one. Did it come up? Which example, Victor? Was that AQA? Halide tests for silver nitrate and nitric acid. Yes, Lorena. Yes. Okay. Let's start with this bit. So draw an X on the appropriate axis of figure 3 when the mixture reaches equilibrium. So equilibrium, essentially, that's going to be the point when none of your partial pressures are changing anymore. That's going to be essentially when your curves are stopped to change. So I'll probably put X around there. AQA paper 2. Fair. Then I don't think disappearing cross is coming up. I think it's going to be your iodine test. Specifically, yeah, iodine test. Iodine clock. Specific heat capacity in terms of graphs, and I don't think it's coming up. I don't think bond habit cycles are coming up this year. If it comes up, it's going to be some sort of definition, or it's going to be something within the multiple choice question. Rechargeable cells, they shouldn't. The way that rechargeable cells are, really, they are a one-time thing. Same with period 3. Yeah, Q equals MC delta T. Raheem, yeah. But I think it's considered an easy topic. If they're feeling nice, then they might throw it in. I want you guys to spend, good question, for your multiple choice, since you have 30 minutes overall. I can't remember what's your overall timing on paper 3. Let me actually double check. Paper 3 is 2 hours. Okay. You have, supposedly, they say 70 minutes on section A and 50 minutes on section B. I want you guys to spend around 40 minutes on section B and completing it all. Okay, complete all of your section A. I would actually say that your section A will be easier. Your writing stuff will be easier than your multiple choice. Get that done as soon as possible. Okay, and then, honestly, get down your multiple choice stuff. Okay, you want to work in the process of elimination. And we'll look at some multiple choice questions in a bit. But let's do this question. Let me put the screen on screen. All right. Period 3, I don't think it came up awesome. I think it came up very minimal. It was there, I heard, but very little. So I think it will come up 100% again. And potentially, I think Group 7 did come up. Group 7 equations can probably come up. Yeah. All right, let's start with this. It says a 0.23 mole sample of carbon monoxide is mixed with hydrogen in a 1 to 2 mole ratio and allowed to reach equilibrium in a sealed flask at temperature T. Okay. At equilibrium, the mixture contains 0.12 moles of carbon monoxide. First thing what I'm going to do is just make a table. Okay. This is my initial moles, and this is my equilibrium moles. Now, originally, if my initial moles is 0.23, and now I have 0.12, what's the change? Well, the change is going to be minus 0.11. Yeah, I know group 7 was, yeah. You can just say it removes like contaminant ions, like carbonates and stuff. What okay. Actually, yeah. It removes like carbonates, like unnecessary ions. Cool. And then, since we don't really have an equilibrium here, actually, no, it says mixed with a 1 to 2 mole ratio. So you're going to start with 0.46 here. Okay, and you're going to start with 0 for your alcohol. Okay, but since this is a 2 to 1 ratio, you're going to lose 0.22. 0.46 minus 0.22. And that gives you 0.24. I'm going to double check that. And then, again, this is going to be plus 0.11. Why are we adding? Because this time it's in the products. We subtract from our reactants and we add onto our products. So we're going to have this as our mole or equilibrium moles for our final. Well, it's 6 o'clock now, so until 8:30. Switch. All right. And it says the total pressure of this mixture is 1.04 times 10 to the 4 kilopascals. I think this one's maybe the wrong question potentially, but let's see. Let's keep going. Calculate the partial pressure in kilopascals of hydrogen in the equilibrium mixture. Thanks, Sams. Thanks. Well, it says we've got the moles of hydrogen. Okay, we need to work out the mole fraction. Well, the mole fraction is going to be 0.24 divided by the total amount of moles added together, which is going to be 0.12 plus 0.24 plus 0.11. Yeah, I know, Bamesy. Yeah, I just realized. I do have. Yeah, the next one I'm doing is going to be the more tricky one. I thought it was this one, but it's just not. But it's fine. It's a good warm up. And then equals to. Well, 0.24. Your mole fraction will be those added together. Okay, which is going to be around 0.51. And then you multiply this by your total pressure, which is going to be this, times by 1.04, times by 10 to the 4. I should probably use this on my on-screen calculator. 0.5106 times by 1.04 times 10 to the 4. And you guys should get 510, 5310, or 5311 if you guys are using exact numbers. Okay. 5311 kilopascals. Make sure you guys are copying across the units correctly. Okay. You guys need to copy across the units correctly. If it's pascals, just make sure it's pascals. Yes, RS. Yeah, basically, yeah. Okay. So work out the mole fraction in equilibrium. Divide by the total, so add all of these together, and then multiply by the total pressure. Okay, that's your partial pressure. All right. Perfect. You know what, while we're at it, let's do the units for this. So the KP pressure, I think most people are probably good at the units, so I'll show you how I kind of go about it anyways. The KP equation, KP is going to be equal to your products over your reactants, so that's going to be PP CH3OH. There's different ways of doing this. You can do PP inside the brackets, outside the brackets. Key thing is you need curly brackets, not square ones. Okay. Partial pressure of hydrogen squared, and then you have times by the partial pressure of carbon monoxide. Okay, what are the units of this going to be? Well, I kind of just label it as x. So I have x on the top, and I have x squared times by x, which is going to be x cubed. Okay, the reason why I'm doing this, I like maths to be fair, but if you go ahead and simplify this using indice rules, from GCSEs, you know that if we divide, we're going to take away our indices. So this gives us x to the -2. But as you can see, our total pressure in the beginning had kPa. So that means that if x is equal to your kilopascals, that means that your overall units has to be kilopascals to the -2. Partial pressure, double P is fine, single P is fine, doesn't really matter. Both are acceptable for it. Okay, it just means partial pressure. Okay. PP is fine. So you can put PP on the outside, you can put it in the inside. It doesn't really matter. The key thing is your curly brackets. Okay, there's different ways that it's taught, but they're all fine. Okay, cool. I want you guys to try this question. This one's a bit more complicated, I'd say, potentially. Maybe. Give it a try. And then give you guys 2-3 minutes, and then we'll go through it. That one, and that was, I believe, 2020, maybe. Paper 2. Which practicals do you think are more likely to come up? Chromatography, I think 100% is coming up. I think this year is going to be gas chromatography or column chromatography, I think. Tiny bit bigger, yeah, I got you. Fair. Okay, and yeah, sure. What organic stuff do you think is going to come? This is KP, Georgia, so you can 100% use it to help you. Chromatography, as I already said, I don't think recrystallization is popping up again, because you guys said there was a nice question on this. The aqueous layer one, I think separating funnel might pop up potentially. Guys, take a note of this, because some of it I've got up in my PowerPoint, some of it I don't. So whatever I'm kind of saying, just put it in chat, just so I can come back to it. Separating funnel, iodine clock test, chromatography, gas chromatography, column chromatography, not normal chromatography. I think maybe even mass spectrometry might pop up, like the actual table. Might be a question on that. Organic tests did not pop up in paper too much. I thought it might have. If it hasn't, then that's bad. That's actually bad. Or even organic synthesis BMZ. Might be some organic synthesis. An aqueous layer. Was it not? Damn. Then potentially, then probably, yeah. If a 6 marker comes up, yes, mass AQA. Mel's potentially, I was thinking about, honestly, I would really think about transition metal, because I feel like this looks at paper 1, and there was decent on it, but not that much. I think potentially there might be some in your multiple choice. I genuinely think there could be. Yes, it's the AQA racks. Yep. All right, let's start with this question. I'm gonna have a quick read of this. Okay, I'm gonna start with the equilibrium expression constant. Yeah, there was a 6 marker on transition metals. I know there was, but I feel like they kind of, was there an equation in there? I don't think there was. Unless was there an equation on aluminium? Because I heard there was some aluminium stuff like outside that 6 marker. Was there? Okay, fair enough then. Potentially to do with amphoteric properties. If there's gonna be your Born-Haber cycle stuff, there might be some your covalent character and your perfect ion stuff. There might be something to do with that. In terms of organic mels, it could be anything. Paper 3, I'm gonna be honest. The way that paper 1 and paper 2 have been going, I don't think there's gonna be much polymers. I think there will be DNA, and we've been going with. I'm planning on doing some DNA today. Yeah, switch, yes. I mean, that's a simple equation. I'm not gonna lie, bro. It's a simple equation. I feel like I think that was a nice 6 marker. If you revise your transition metals, I feel like that would have been a good one. Was DNA like DNA? No. That's not DNA. That's biochem. The DNA and your amino acids, they're slightly different spec points. So I heard, as I've heard anyways, like there was your alpha and beta structures of your proteins and such. That doesn't necessarily link to DNA in terms of chem anyways. Both, I say, both. All right, let me start with this here. I'm going to start by making the Kp equation. I think Kp and Kc will be quite prominent. There will be one big marker on it, at least one of them. Not both, but there will be one at least big one. But Kp is going to equal to Pp of your oxygen times by your partial pressure of your sulfur dioxide squared divided by your partial pressure of sulfur trioxide squared. Okay. Well, your partial pressure of your oxygen is going to be the same thing as your mole fraction of oxygen times by the total pressure. So well, we don't actually have the total pressure, which is going to be, that's what it's essentially asking us to work out. I'm going to call this X, okay, like so. Same thing for this, times by your mole fraction of SO2 times by X, and that's squared, divided by your mole fraction of SO3 times by your pressure, also squared. Now we need to clean this up. Can we not cancel out the P? It doesn't work like that, RJ. It doesn't work like that. I wish it did, it didn't. It's... Okay. Now, we need to work out what the mole fractions of each of these are. Now, the mole fractions of your oxygen is going to equal to your 0.6 divided by all your mole stuff added together. And actually, I'm just going to put this right into the calculator. I'm going to make a new table here. What do you mean? What do you mean by the P, guys? What do you mean by the P? What does that mean? Are you saying I'll get rid of the partial pressures here? Because if you do that, it doesn't really make sense. Because that just means that represents partial pressure. It's not really a number. Yeah, thank you, Farah. Total is 2.12. Thank you. So, do we not square it? It turns into 1p. I think I know what you're saying. That's the top and bottom p. So yeah, 1p left on top. Ah, okay. Yeah. Basically, yeah. Yes. By p, I'm assuming you mean pressure. I'm assuming you mean pressure. But yeah, exactly that. We'll look at that in a second. Okay, I'm gonna work out the partial pressures out. Farah said it was 2.12 for total. Cool. And that's gonna give me 0.283 for my oxygen mole fraction. 283 X times by, and then we're going to do the same thing for the rest. The partial pressure for sulfur dioxide is going to be 1.2 divided by all of it, and then you're going to do the same thing for sulfur trioxide as well. So that's going to be 0.566 X, but this is all squared, all divided by sulfur trioxide. X represents your pressure, okay? Because we don't have pressure, right? When we are working out our partial pressures, we take our mole fraction and times it by the total pressure, but we don't have total pressure, so I've just called that X, okay? And then 0.32 divided by 2.12 again, and that's going to give me 0.1509. 0.1509 X. Again, this is squared. Now you can see that if I kind of expand this out a bit, 0.283x, and I'm actually just going to call this squared, divided by 0.15, I'm going to round this to 0.151x squared. You can see that this is an x squared and this is an x squared here. When you have two things that are being multiplied, what happens, you can actually just go ahead and cancel them out. Okay, you cannot cancel stuff out if it was a plus. Okay, you can't do that. You can only cancel stuff out when it's being multiplied. Okay, like so. And what you're essentially left with is your total Kp, which is given to you as 7.62 times 10 to the 5. 7.62 times 10 to the 5 is equal to this expression. And you can go ahead now and solve for pressure. What's the percentage for an A? For chemistry, I'm predicting it around 71. I think it's going to go down this year for chemistry from the way it's been going. I think chemistry A star for AQA will be potentially even 80%. Yeah, I think it'll be around 80%, potentially even 79, around there. I think that's 71. I know 71 is high. I know it's high. But but in comparison to, okay, if I do, let's say 79 or even 80% for an A star, minus 10%, usually it's around 10%. For a B, each time just take away 10%. Last year was at 82.3%, 82.6% around for an A star, but it's going down. OCR, I think it's still going down, but I think it's the way it's been. I think I've heard really, really good responses overall. I think it might even stay the same, even or less. So I'm gonna predict around 89% to 90% for an A star for OCR, which is still pretty high. Like from what I've heard, it's been crazy. It was 66% last year, was it? Yeah, last year's I've seen OCR's last year's paper BMZ. I'm telling you, they're actually they're very, very light. Anyways, let's go ahead and rearrange this for your pressure. 7.62 times 10 to the 5 times by 0.151 squared divided by 0.566 squared, and I'm also going to divide by 0.283. Your total final pressure should be 191,641. And then this is in pascals, I'm going to assume. It is in pascals. Okay, and we can always convert to kilopascals. That's going to be 191.6 kilopascals. Light work, light work. Alright, let's keep on going. Using that info, I want you guys to try this. We're gonna look at more difficult stuff. Alright. What do you remember about this then? What do you remember about this? These are actually going to be your... It's technically your thiosulfate. It's not your thiosulfate one. It's technically part of a practical. It's part of a practical, technically. These are catalyst equations. I think they'll pop up in some way. Okay. I want to go over the heterogeneous catalyst script. Give this a try. And then see what you can remember in terms of the equations. Hi Rico, hi Rico. I started live at 5:30. Saying I think period 3 is gonna pop up. I need 2 equations, guys. 2 equations. There are 2 equations you need to know about this. Okay, you good? So because they're the same charge right now. Oh, Farah, be careful there, yeah. Because they're oppositely charged. What happens is they repel, so your activation energy is higher. Okay, and that's where your Fe2 plus ion comes into play. That's fine, Fred. I mean, yeah, that's calm. It's calm. One sec, guys. Okay. The 2 equations you need to know about this year, because you're using Fe2 plus ions, these essentially, because they are, sorry, not opposite charged, they're samely charged. I made that same mistake, that's my bad. Because it's samely charged, negative and negative, they repel. Okay, we don't want that. Whereas Fe2 plus and any one of these ions, okay, they are oppositely charged, so they go ahead and react, and that causes your activation energy to go ahead and decrease. And these are the 2 equations you need to know for this, okay? S2O82 minus, okay, plus you're going to be using your Fe2 plus, okay? And this makes the following. This makes 2SO4 2 minus and iodine, and you're going to be using 2 Fe. Actually, sorry, not iodine. I don't know why I said iodine. 2 Fe3 plus. Okay. Remember, if you ever see some sort of redox titration, I don't think you will in paper 3. But if you ever see Fe2 plus, just think that Fe2 plus goes to Fe3 plus. Okay. Use that rule. Okay. Similarly, because we want the Fe3 plus to go back to Fe2 plus, why? Because it's a catalyst. We can actually just almost just substitute that in straight away here. Okay. And what have we not used? We haven't used the iodine yet. 2I minus. Or 2I minus goes to I2. Okay, very, very simple. You're just using I and ions, and you're just using your reactants and your products. You don't even have to memorize these. You can kind of just figure out on the spot. Okay, so S2O8, 2 minus goes to your 2 sulfate ions, and then your iodide ions goes to your iodine. Okay, pretty simple. Cool. Now your heterogeneous catalyst script, I think this is something that's potentially likely to pop up as well. I want you guys to get this down word by word. Okay. First of all, what you're going to do is write down hard on the side. Okay. Heterogeneous, that's going to be the first word. And specifically what we want to write down is a definition of heterogeneous. How do you know when to add 2 moles? You can use it to kind of balance the charges, I guess. But it's just 2. You just need to put 2. That's all. Okay. I can't fully give you a. I'm just trying to think of the reason for this. Usually it's just 2. Okay. No, you're gonna need 2. That's all. Alright. Heterogeneous catalysts. This is different. This is separate script. Separate. This is homogeneous. Yes, this is homogeneous. Yeah. This is separate script. Okay. For heterogeneous catalysts, we need to write down our definition first. What does heterogeneous work? What is heterogeneous? It's going to be a different state to reactants. Okay. Now your A is going to be adsorption. What is adsorption? It's not absorption. It's AD. So adsorption means that it's going to essentially go ahead and attach to the surface. So essentially what you have is you have some sort of surface with your catalyst attached to it. You have some reactants flying about, and they go ahead and get adsorbed onto the surface, like so. Okay. What happens is your bonds get weaker or your bonds get rearranged. Get weakened by catalysts. Okay, next one's going to be a reaction. Your reaction actually occurs between your reactants. Why? Because the catalyst has decreased your activation energy. Okay, and lastly, desorption, which is essentially just release of your two reactants, release of reactants. Okay, I should probably also say here that new bonds form. Okay, release of products actually. Okay, one thing to also mention is the poisoning of catalysts, and they can ask about this. So poisoning of catalysts is that if there's any sort of impurities, okay, and this is very similar to your biology stuff if you do biology. The poisoning of catalysts is that there might be impurities in the catalyst, and that just means that its active sites are blocked. Okay, if the active sites are blocked, that means they can't access the reactants. So reaction, or you can say activation energy, doesn't decrease, or reaction does not speed up. Okay, you can talk about something like that. Okay. Competitive inhibitors. This is going to be a heterogeneous catalyst script. What's the word after catalyze? Catalyst? Poisoning. What's the word for reaction step? Oh, catalyst decreased. Catalyst. Yeah, catalyst decreased your activation energy. Okay, I'll slightly zoom out, guys. If you want to get that, that's my bad handwriting. That's my bad, guys. You want to do thermodynamics? We will look at some Gibbs in a bit. I'm gonna want to look at some electrodes really quickly, some DNA stuff, some chromatography stuff, and then we do thermodynamics. The graph. What do you think Gibbs is popping up? Did Gibbs pop up in paper 1 or no? What causes impurities? Soups. So impurities in catalyst causes the poisoning. You just call it poisoning. Absorbed onto yes, sure, exactly. Yeah. DNA came. Gibbs came up. Yeah, if Gibbs came up, then I doubt it. I'm gonna be honest, man. I'm honestly predicting that Born Harbor's not come up. Born Harbor's not coming up. I'm telling you, it's not, bro. You're 4 whole questions, and they want to make it hard. If they give you a Born Harbor cycle, that's literally a free one. Protein came up. That's alpha and beta structures. DNA is different. I'm telling you this stuff, bro. That's not related to DNA and drawing bases. Drawing bases hasn't come up in ages. We'll look at it though. We'll look at it. I went over in my paper one stuff though. I went over time of flight and I went over. Don't worry, bro. I think KC and KP, one of them at least. I think they will be. My prediction is there's going to be an iodine clock test, but you know I'm also going to throw in specific heat capacity as well. There's going to be some sort of rate determinant step in your multiple choice. Time of flight coming up in multiple choice. Alright, let me continue the plan of the thing, bro, and then we'll move on, man. I promise we'll get to it. Actually, no, I don't promise. I take that back. Okay, this one. Electrodes. Electrodes popping up, bro. Let's be real. The one thing that's popping up is electrodes. Did it come up paper 2? Did rate determinant step pop up? That's why I need to see the papers, bro. Tilly, yes. Not colorimetry, but calorimetry. Cal. It's two different things. Okay, so it's A. So calories. Yes, essentially though. Alright guys, attempt these 2 questions. If you've got the answers, mention it in chat. And then we'll go through this. Because electrode is popping up. There's no way electrode's not popping up in a multiple choice question, bro. I'm gonna be real. I'm gonna be real, man. I made like a little list a while back. If you guys on Discord, I did make a list about like what I think is gonna be probably popping up. Oh, we got 2 different answers. We've got chlorine and we've got Fe2 plus Cl2. The answer is actually silver plus, guys. No, I'm joking. It's chlorine. Well done. For the guys who said chlorine, perfect. How do you know when it's going to be the negative or positive? So essentially, this is the way I remember this, right? The most positive is the best oxidizing agent. For me, electrodes is the worst topic, and this is the biggest reason. I always forget which one's the what's it called? Which one's the oxidizing agent? Which one's a reducing agent? Okay, I always forget that because of the positive and negative. This is like the best way I could figure out. If you guys have a better way of memorizing it, then great. In my opinion, for me, electrodes was actually my worst topic throughout the whole of A levels. I think people find it quite easy, which is great. It was my worst topic. But yeah, this is going to be your oxidizing agent. Now, your oxidizing agents are going to be on your left. Okay, your reducing agents are on your right. Now, reducing oxidizing agents, essentially what oxidizing agents means is being reduced. And being reduced using oil rig, using the definition of oil rig, it means gain of electrons. That means that these are being reduced, meaning that these are your oxidizing agents. Okay, which is the best one? You're going to be using the most positive O and O. Okay, well in that case, which one, RJ, which one is going to be your worst reducing agent? Which is your worst reducing agent? If you guys want to answer this in chat as well, what is your worst reducing agent? One, I like that, Farah. Weakest oxidizing negative, most negative. I mean, fair. Oh, we got some answers. We got Cl minus. Okay, first of all, we need to identify. We talk about reducing agents. Okay, so we're not looking at the left hand side. So if you guys, if you said Cl2, you will not get the mark. Okay, it has to be one of these because you're talking about reducing agents. Okay, reducing agents is going to be on the right hand side. Oxidizing agents is going to be on the left hand side. Okay, so it can't be Cl2. Some of you have said Fe2 plus, which is in the middle, so I'm unsure about that. And why is it Fe? It does say Fe2 plus. Either it's going to be Fe solid or it's going to be 2Cl minus. Okay, so if we know that on the top is your best oxidizing agent, okay, this has to be your best reducing agent. Sorry, that's wrong. It's going to be your worst reducing agent, which is going to be that 2Cl minus. Yeah, I don't know why I said Fe2 plus. It's CO2 Cl minus, or just Cl minus actually you can put. Okay, it just swaps over. Your best oxidizing agent means it's going to be your worst reducing agent. They are the opposite. Opposite. Because look, oil rig, your oxidizing agent means it's reduced, right? It means it's reduced. That means you gain electrons using oil rig. Do you agree with that, RJ? Right? And that means that if it's the best at gaining electrons, that means it's the worst at losing electrons. Yes? If you're the best at something, if you're the best at winning, you're the worst at losing. Yes, RJ, yeah. Okay, I mean that's a cold analogy, bro. That's a cold analogy. Alright, but to be honest, these type of marks they'll pop up here and there. I don't think it's gonna be a major question. I don't think. Yeah, I have a fan on right here, bro. I can't function either, bro. But you guys have one exam left, so like you're nearly done, guys. Write the conventional representation for the cell using the standard electrode potential for the conversion of tin ions to tin. Okay, so we're gonna be using. Ooh. Okay, they haven't given it to us, which is fine, I guess. Tin ions to tin. Well, that's just gonna be Sn2 plus 2 electrons is gonna go to Sn. My fan is the size of an exam paper. I think it is. It might be bigger, bro. It might actually be bigger. But with the standard electrode potential, the thing is, this is the key word here, standard electrode potential. Is it? Am I blind? I am blind. Oh shit, my bad, my bad. Yo, you're gonna have to remind me what RP4 and RP11 is, bro. I'm a bit real. I don't remember them off the top of my head. Yes and no. Roper, I'm gonna explain that. Okay, so when we talk about standard electrode potentials, and I can actually see this popping up as well, if they ever ask you to draw the diagram between your standard and some sort of in this case tin, let's say, okay, when using standard you need to be using hydrogen. Okay, so in this case your cathode will be, is it cathode? Your electrode, I should probably say, your electrode is going to be platinum for hydrogen. Okay, you have a solution with hydrogen ions, specifically 1 mole per decimeter cubed. Okay, and you also add in hydrogen gas. Okay, that's going to be your diagram for, that's the other, sorry, wrong way around. That's going to be your diagram for your electrode. Okay, in the case of your other diagram, you use tin. And hydrogen should be on the left. BMD, hydrogen always on the left. For your standard, hydrogen's on the left. For standard. No. When it's standard, I know what you're saying is right, specifically because of this, and you're trying to flip it. But that's the whole reason why we get minus 0.14. Okay, in your standard ones, your hydrogen's always on the left. And that's the reason why this equation is made in the first place. That's the reason you get minus 0.14. Because hydrogen's on the left. Does that make sense? Now, if we use the electrode here, which is going to be tin, should probably technically it should really be in the actual solution itself. This is not going to work. There we go. That's tin. Okay, that's going to be Sn2 plus. Again, this should be 1 mole per decimeter cubed if you're doing standard solution. And then you have your salt bridge, specifically potassium nitrate salt bridge. Okay, and then you're going to connect your 2 electrodes together with a voltmeter, like so. Okay, in a standard electrode, and you can Google this if you like. Hopefully, if I'm wrong, then tell me I'm wrong. But yeah, in a standard electrode, no matter what, your hydrogen one is always on the left. That's the definition of a standard electrode. Okay, all these equations you're getting here, these are all tested against hydrogen. Okay, this is the standard electrode E values, your EMF value. These come from testing against this. Okay, and the reason why we use platinum is because we use hydrogen. Okay, and yeah, your standard conditions are going to be 100 kilopascals and your room temperature, which is 298 Kelvin. Okay, you will get away with 25 degrees Celsius, but you should be using this. Why is a H plus in the solution? Good question. It's just the part of the hydrogen electrode, essentially. Okay, now this is how you're gonna, if the source of H2 like you showed, isn't it 0.5? No. So essentially can big. It really depends on the because technically it's an acid, right? Yeah, we'll do the cell notation. It's Victor. It's a salt bridge. So that's the salt bridge that you normally use. If it's the source is a gas, so it's not H2 gas. It's the actual. Yeah, if you guys want to try the cell representation and then use it in chat, say in chat, definitely, go ahead. Why is you guys have a lot of questions, which is good, which is good. Why is potassium nitrate used as a salt bridge? Specifically to allow ions to move, not electrons. Ions. Is it ions? Electrons. It's ions. It's ions. Let me double check that. I believe it's ion. Don't use silver. Don't use silver nitrate. Use potassium. Does KN3 salt bridge allow ions to? It's ion, isn't it? Yeah, it's ions. Yeah, gotta trust myself, bro. I know my stuff. Yeah. Yeah, completes the circuit essentially. Yes. Yes, it's platinum. Yep, that's platinum. Yes, Jibs. All right. Now, the reason why we don't use so actually, if you ever ask you about the reactants, if you ever ask you about a reagent for this, put HCl. Okay. Technically, you can put H2SO4. Okay, but the reason why you don't use H2SO4 is because what happens if you do decide to use H2SO4, you're gonna actually have to use 0.5 moles per decimeter cubed. I don't want you guys to do that. Okay, I don't want you guys to do that. Use HCl. It's a 1-to-1 ratio. It's simple. If it ever asks for the reagents for your hydrogen stuff. Okay. Now, in terms of your standard electrode, or sorry, your conventional representation, you want your solids to be on the outside, meaning your cathode. So what your cathode's made of? Well, on the left-hand side, we keep it on the left, platinum. Platinum is our electrode, and on the right-hand side, we have tin. And we're going to separate it with a line, a vertical line. Now, your vertical line represents a state change. Okay, everything that is. Why tin not on the left? Because tin is just on the right here. That's why. Okay, so whatever in your diagram, you just copy it across into your conventional representation BMZ. Okay, I know in the equation, I know that is it's getting reduced. It's getting reduced, right? This is getting reduced. Essentially, whatever you have when you're working with your standard electrode, you're always going to put it on the left. Hydrogen's always going to be on the left. I would try to Hilal. Okay, it's better to. I don't think you lose that mark. Just be careful with that. That's it. RJ, be careful. Be careful. And the thing is, BMD. The reason why it's negative is because this is what gives us a negative voltage. Okay, this is what gives us the negative voltage. All right. Now your platinum and your tin should be on the outsides. Okay. Now each line separates your what does it separate again? Your state symbols. Well, what do we have? We have some sort of solutions in here. So we have H plus in here. Okay. Separate that symbol. Actually, not even H plus. We're gonna do H2 first, and then H plus. The reason why we do that is the stuff with the variable oxidation states or some sort of charge will always go towards the middle. Okay, bring that towards the middle, and your H plus is going to be aqueous, and this is going to be gas because the different state symbols they will be separated with a straight line. Okay, in the case of this, we only have SN2 plus, so I'm just going to put SN2 plus here with the aqueous, and then a straight line, or actually there should be a double line in the middle because that's our different electrode system. Okay, it would be on the right if it was reacting with something that's positive. Yes. Okay, whenever you have standard electrode, this only applies for standard electrode, you will have hydrogen on the left every single time, BMZ. Okay, it could come up as drawing, it could come up as a one marker in your multiple choice, it could come up in anything. Okay. In terms of your reason for potassium nitrate, just use potassium nitrate. Just say allow ions to move. Okay. You don't need to necessarily know why. It's just one of the reagents or one of the usages of it. Okay. If you ever, for example, had something, I'm just trying to see, not necessarily in this table here, but sometimes what you can have is like maybe hydrogen peroxide goes to stuff like, actually, no, hydrogen peroxide is not a good example. What's a good example? Let's use iron chloride, for example. Okay, this goes to Fe2 plus and chloride ions. What happens is you might have a solution with Fe2 plus and chloride ions. Okay, and they might be both 1 mole per decimeter cubed. So if you're ever writing your what is it called? Your conventional for this, let's say the electrode is iron. Okay, iron's going to be on the outside. Now your two aqueous ions are going to be your iron 2 and your chlorine 2. So what you're going to do, sorry, chlorine 1, you're going to bring them all closer. You're going to bring the thing that's closer with the charge, and then you're going to put a comma, chlorine minus. The reason why, both these are both aqueous, they both have the same state symbols, and you would do it like so. You don't have to put platinum no only if it doesn't have a what is it called, an electrode itself. So in this case, this is actually a very good example. You can see that iron chloride goes to Fe2 plus and Cl minus. Well, iron chloride is essentially a solid, or it's your ionic lattice. But if you ever don't have a solid that is made, then you have to use platinum. How do you know the order which goes from left to right? On the outside, this has to be a solid. Okay, that's your electrode on the outside. Okay, on the inside, every single line represents your change in state. And the closer towards the center, okay, the closer it is towards the center, make sure you have a higher oxidation state. Okay, so you can see 2 plus is higher than minus, so just put that towards the center. This is not from my past paper, maybe. ROOR. What does that mean? What does ROOR mean? What does that mean, guys? Faiz Shah. Faiz. Alright. I want you guys to try this. I think this is a trickier electrodes question. Reduce, oxide, reduce. Ah. No, that's a good way. That's a good way. That's a good way. Try this question. I think it's actually a pretty interesting question. Is it worth 2 marks? Nope. But it's pretty interesting. Do I do the hydrogen thing for everything that is metal or not platinum? Or is that just a hydrogen cell? That's just a hydrogen cell, but if it GLO, if it doesn't have a solid or some sort of electrode in the equation, then you're going to be using platinum. Calm Dean, get back on it, man. Get back on it. Still here, bro. Appreciate it, Saifola. Managing the TikTok chat. Appreciate it. You guys tell me. Tell me. Use the rule. Okay, think about what's your strongest oxidizing agent first, and then that will help you work out what's the kind of the best reducing agent. Okay, use that to help you out. All right, good. So your most positive. Wait. Your most positive is your best oxidizing agent. Okay, but the question's asking us in which hydrogen peroxide acts as a reducing agent. Best oxidizing agent. So from this, which one is going to be your best reducing agent? Because it says hydrogen peroxide has to act as a reducing agent. Well, in this case, you can see that this is acting as an oxidizing agent, so it can't be this one. Okay, so we have to use this first equation somehow. Now, you have to think about, well, which equation can your H2O2 reduce? And it's really to think about what is your best and worst reducing agents. You'll know more about dairy products. That's funny, man. I heard about that as soon as the exam finished. Mad. That's actually mad. You're gonna flip the first one, and it's gonna be oxidized. Yeah. Alright, which one? Which one though? So we've identified that this is the best reducing agent. Okay. Probably we're not gonna be using the second equation here. Probably not. Actually, it's not the best reducing agent. I take that back. That's not the best reducing agent. But in this case, because H2O2, we want to reduce with oh, okay, guys. We're not actually going to be using the VO2. We're not using this. The reason being, I know you guys have been taught. Normally pick the one that's less voltage. We're not going to be using this equation. We're not. The reason being, this is the main reason. Okay, if your most positive is your best oxidizing agent, the more negative you get, the better the reducing agent. Right? Now, if it's the better the reducing agent, that means that V3 must be a stronger reducing agent than H2O2. V3 plus must be a stronger reducing agent than H2O2. Therefore, your H2O2 cannot reduce V3 plus. It cannot reduce that equation. So which equation are we left with? This one here. So if you use VO, yes, exactly, Ibrahim, exactly. We don't want VO to be the reducing agent. Okay, we want hydrogen peroxide to be the reducing agent. Okay, so I'm not saying it's not possible to reduce, but because the question is asking us, we want the hydrogen peroxide. It is, Hasib. Essentially, it is. But because we want H2O2 to act as our reducing agent, we want it to be on the left-hand side of the equation. We cannot pick V3 plus. We cannot do that because specifically, as V3 plus equation is more negative than 0.68. Let me use with my mouse. But since 0.34 is more negative than 0.68, and since the more negative you get, the better the reducing agent, your V3 plus must be stronger than your stronger reducing agent than H2O2. Shall I repeat that one more time? I'm gonna start again. I'm gonna start this part again. Right from the beginning. Your most positive is your best oxidizing agent. Yes. Therefore, your most negative is your worst oxidizing agent, or we can say your best reducing agent. Do we agree? Calm with that, yeah? I'm gonna say yes. That's a yes. Okay. Next, since we want H2O2 to be our reducing agent, and we know that V3 plus is more negative, V3 plus is a better reducing agent than H2O2. Yeah, exactly, Ibrahim. Exactly that. Okay. So your H2O2 can't reduce your V3 plus. It just can't. It doesn't work. Okay, it just can't reduce that equation. So the one you have to pick can't be this one. We're not going to be doing this one because that's your oxidizing agent. So what you're left with is going to be the first and the last. Okay. Can you guys go ahead and balance this equation with this electrons and make me a single equation? Please do that. Both. It doesn't really matter. These are electrodes that can pop up. This is actually, I think, more of an OCR style question anyways. Either way though, it's electrodes. Why is it oxidizing? It's because H2O2 is at the left-hand side. That's why. It's an oxidizing agent, RG. Keegan, I think probably iodine clock or specific heat capacity. I want to look at some DNA stuff after this electrode stuff because honestly, I'm not a fan of electrodes. It's just how it is, to be honest. But it's gonna pop up in some way or form. Okay, this is gonna be your best friend. Okay, Like, get your definitions. Just this is gonna be your best friend. If this pops up, I call it a long day. It's peak. It's just really long. But I'll show you the iodine clock stuff in a second, RJ. Fuel cells, nah, it's not popping up, bro. I'm not doing fuel cells. I hate that topic, man. Man said fuel cells. I know it's for 2 months. It's just a bit long. Anyways, though, rates. You want to do rates? Yeah, fuel cells, they did come up. What specifically in rates, Mikhail? You want to do like the table stuff? Because I know our Arrhenius equation, they came up though. Yo, I love fuel cells, bro. I love fuel cells. I hate that. Nah. By fuel cells, she means like hydrogen fuel cells and table stuff. Okay, yeah, I do have some of that in my old PowerPoint. I'll bring that up. Okay, table stuff. Okay, yeah, sure. We'll go with that. Okay. Yeah. All right. In terms of balancing this, we have 2 electrons on the top and we have 5 electrons on the bottom. We're probably going to be timesing the first equation by 5 and the second by 2. We should probably flip the first equation first, though, like so. So I've just gone ahead and flipped this equation. The second equation we have is MnO4 minus plus 8H plus 5 electrons makes Mn2 plus 4 waters. Just make sure your electrons are on the opposite sides of the equations. I'm going to multiply this equation by 5. I'm going to multiply the bottom equation by 2. And if I go ahead and combine this together, I end up with the following. 5H2O2 plus 2MnO4 minus plus 16H pluses. And then if we times the other side as well, that gives us 10 hydrogen pluses plus 5 oxygens plus 2 Mn2 pluses and 8 waters. But what we need to do is cancel out anything that's on both sides of the equation. We have a 10H plus and we also have a 16H plus. Well, you can see that I can just remove this. This becomes 6, and that will be your final equation. Okay. Wait, reducing agent is oxidizing, so it has to be on the left. Reducing agent is on the right, oxidizing agent is on the left. So oxidizing agent, you can learn it like this, RJ. Oil rig. Okay. Oxidizing agent means reduced, and reduced means gain of electrons. Well, you are essentially adding electrons here. Okay. So if you're adding electrons to your reagents, this must be getting reduced. Therefore, it's an oxidizing agent. Okay, you can think of it like that, RJ. UB, good question. We might have a quick stop at maybe 7, maybe half 7ish, like for 10 minutes, because I'll go pray Asr real quick. I haven't prayed yet. But yeah. Okay. Cool. Very, very nice. Actually, that's not nice at all, but let's move. All right, this question here. If you want to draw yourself a diagram, go ahead. Simple 1-2 markers I can kind of pop up here and there. I wish I could probably. I don't actually have any resources in terms of the practical stuff. A lot of it will be in past papers. I do have an iodine one, but I'll kind of walk you guys through in terms of what is specific heat capacity stuff, in terms of the details behind it. But in terms of actual question, I was looking for one last night. I just couldn't really find one that I really wanted. There is one out there, 100%, but it's on like Exam Pro and stuff like that. And as a private tutor, I just don't have access to it. I wish I did though. But if anyone wants to hook me up, man. Actually, in terms of vanadium, what popped up in terms of vanadium? Because I know that vanadium popped up in paper 1. Did it have zinc? Was there zinc or not? Because I know in terms of DNA and cisplatin, you guys don't really look at cisplatin that much. But okay, we'll go over this anyways. No zinc. Okay, we'll quickly go over zinc then. All right, that might potentially pop up. Well, was there? No, it's not vanadium then. That doesn't count as vanadium. That's contact. That's contact process. Technically, I guess you can count it as vanadium, but I wouldn't count that as a vanadium topic. I wouldn't count that as catalyst topic. Okay, We'll go over some vanadium stuff here in terms of V2 plus, V3 plus, V4 plus, and V5 plus. 1 second, guys. Okay, cool. Dean, next year. You guys allow it, bro. Wait till results day. Chill out, man. Enjoy your summer. Do your paper tomorrow and just relax, man. Was there a whole question of vanadium? Was it? All right. In terms of this, whoever said ligands, the chlorine ligands, yep, these are the ones that are gonna pop off. So essentially, what will happen is you will bind with the platinum, and remember these are additive covalent bonds since they are ligand replacements. So what happens is you end up with something like this. Okay. And they are additive covalent bonds. Okay, plus 2 Cl minus. If you put that down, that's up to you. That's optional. All right. Cool. We'll go over some vanadium stuff anyways. If there was nothing on zinc, then I'll quickly go over that. Because essentially to oxidize vanadium, or to reduce vanadium, I should already say. Yeah. Good question, RS. Very, very good question. Does it bind to cytosine? It can. Essentially, why that happens is chlorine bonds. Simple answer. Chlorine bonds and chlorine to platinum bonds are weaker than platinum to nitrogen bonds. That's the easy answer. But your NH3s will essentially help in terms of preventing your DNA replication, and that's kind of spoilt the second question here. It distorts the shape. It distorts the shape of your DNA, okay, which prevents DNA replication. And the whole point of cisplatin is to prevent, cancer cells, from replicating again and again. So it prevents DNA replication. Yeah, exactly. Oh, you keep thinking about methylation. Yeah, bio's finished, bro. I remember epigenetics. I actually really like that topic, though, Shah. I really, really like that topic. Alright, you know what? We're gonna go on sidetrack for a bit. Vanadium. Nah, Mikhail, you won't get the mark for that. Talk about distorting the shape because specifically it prevents your DNA replication. So it talks about like if you want to go into biology and stuff, it's to do with your not DNA helicase, DNA polymerase. That's it. That's the enzyme. Okay, it's to do with this enzyme, and it can't just keep on going because it just doesn't fit because you have this random chunk here, so it just won't fully replicate. Okay. All right. Colors. I'm assuming you guys did have colors that probably came up. But this is how I kind of remember this. You better get vanadium. Is there a V5? Am I tripping? Is there a V5? That's the other way around as well. Crazy. 1 second. Sorry, guys. I've forgotten this, and I should not have forgotten this. It's my bad. V5, V4, V3, and V2. And what I'm doing essentially is I still have chemistry notes on my wall. I'm just looking at them. From like a year back. Yeah, cool. Shit. Okay. You better get vanadium. Okay. V5 is yellow. V4 is blue. V3 is green. And V2 plus is violet. Yeah, my bad, guys. My bad. Yep. Okay. Cool. Now, in terms of the actual molecules, you guys do need to know some compounds. V2 and V3 plus they normally say the same. Okay, that works. Yeah, that's a good one. V4 plus, well, that's going to be vanadium. Let me see if this is a 4. That's going to be just like so. Yeah, just going to be VO2, and this is going to be VO2 plus. I don't know why, Farah. I don't know why. Like a lot of the stuff is just there. Like specifically like the stuff that I need to memorize. Yeah. Wait, AO2 is good, yeah? Come on, BMD. Come on. Alright. That's essentially your oxidizing well, compounds anyways. But in terms of actually going from VO2 plus, because you need to know these compounds by heart, by the way. And this should actually be 2 plus here, sorry guys. Sorry. There we go. That's fixed. Get that down. Okay, VO2 plus and VO2 plus. You need to know these compounds, and you need to be able to essentially go between these using zinc. Now zinc goes ahead and turns into Zn2 plus and 2 electrons. You also need to know this. Okay, and for example, let's say I want to go from V2 plus to V3 plus. How can I do that? Okay, well, I can make a half equation like so. V2 plus goes to V3 plus and 1 electron, and you can see I can start to balance and combine these two equations together using my half equation knowledge. Okay, and I don't think this is actually a very difficult topic. It's just knowing the fact that zinc goes ahead and reduces it. Okay, so what do we need to do? If I want to keep V2 plus on the left hand side, I'm gonna flip this equation here. So this becomes V2 plus. I should probably times this equation by 2 actually. 2V2 plus Zn2 plus goes to Zn and V3 plus, like so. Oh, sorry, that should be a 2 there. Okay, do you understand what I kind of did there? So I've times this equation by 2 on the bottom. Okay, this goes to 2V2 plus 2V3 plus 2 electrons. And then I've swapped the other equation around and then flipped it. And then combined them together. Okay. I want you guys to try the same from V3 plus to VO2 plus. Okay, and I want a combined equation. Okay, give me a combined equation from V3 plus to VO2 plus. Okay, what is a full, in fact, yeah, what is a full redox equation for this? Yes, actually, yes, of course. And then after this, what we're going to do is drawing of DNA stuff, dehydration mechanism, chromatography, and then some other stuff if we have a bit of time. Just looking at time as well. We have 1.5 hours. We have some time. And probably should. What did I say? Yeah, okay, yeah. After this, dehydration mechanism, then chromatography, then iodine clock. Come on. Yeah, again, Marwa, thank you so much for that donation there. Literally, it means a lot. It means a lot. Oh yeah, multiple choice question. Yeah, yeah, we'll do that. All right. Once you've got that, try this question. I want the full equation for this. Young, incorrect. I need zinc. I need zinc in there. I need zinc. Use zinc. 3.5. What do you mean 3.5? Yo, listen, chill out, bro. Chill out. You don't have to give me anything, bro. I appreciate all what you guys have given me. This is technically yes, transition. I told you. So reduction of vanadium, use zinc. Bro. It depends on exam board as well, though. It actually does depend on exam board. Which exam board are you doing, bro? Because in AQA you use zinc. Let me actually double check. Reduction of vanadium by H plus, because I believe you can probably use H plus as well. Which is actually, I believe, valid. Let me just double check for you. Yes, you can use H plus. You can use H plus. Bro. Oh, you do AQA as well. Zinc works and H plus works as well. Okay, usually it's going to be zinc though, I'm going to be honest. Okay, the reason why you zinc and H plus together, the reason why you get H plus, Prav, is because of your redox half equations. Okay, the H plus comes from, well, I'll show you how this actually works. Okay, if you guys have already started, it's great. Let's actually start by balancing our this redox equation first. I'm going to put Zn on the top here, which goes from Zn to Zn2 plus 2 electrons. Okay. Now what we have here on the side is we have 2 oxygens on the bottom. So what I'm going to do is add 2 waters on the left hand side. And now you can see that now we have to add our H pluses. That's our essentially the acidic conditions. So that's going to be 4H plus, like so, on the right hand side. Now what we need to do is balance our equations. Well, at the side, on the left hand side here we have 3 pluses. On the right hand side we have a 5 plus. How can we balance this? well, we just use 2 electrons. And now what we want is, because we want to keep this equation the same, well, because we're going from V3 plus to VO2 plus, like so, I'm going to actually flip this equation. So I end up with V3 plus 2 waters plus Zn2 plus goes to VO2 plus 4 H pluses, and that's and plus Zn. Okay, it all depends on the order. Sometimes you can go from this to this. It doesn't really matter. It really depends on what they're asking for. Do it with H plus pref. Okay, it all depends. It all depends on your redox equation itself. Okay, because V3 plus to V2 plus doesn't include H pluses. There's no H pluses pref. Okay, here there's no H pluses. The only reason why there's a H plus is because it's redox reaction. The reason why I flipped it, Maz, is because you can see that electrons are both on the same sides of the equation. I don't want that. I want to be able to cancel my electrons, so I need to flip this equation the other way around. Best way to get full marks in mass spectrometry, and it's spectrometry. Key thing to know about mass spectrometry is, one, the one with the highest peak is going to be your mass number, and two, the other ones that you have will be to do with the isotopes of the actual molecule. So sometimes you can have chlorine 35 and chlorine 37. I talked about this before in my paper 1, I believe. And for example, let's say you have a molecule, right? Like so, you can have essentially 2 isotopes of this, which you can have chlorine 35 and a chlorine 35, which has a mass number of, I don't know, 35 plus 12 plus 12 plus 4 plus 2. This has a mass number of 65, whereas you can also have an isotope of 35 and 37, which now has a mass number of 67. You can also have an isotope with 37 and 37, which could be 69. Okay. Why can't you cancel it? Because it doesn't work like that. Let's say you have 2 waters on produce, and also if you just add these 2 equations together, like, you end up with 4 electrons on the right hand side. Okay, you can't cancel anything out because you don't have anything on the left. It doesn't work. You need to flip it. All right. Fragments, yeah, it can be to do with fragments as well. Why do I only flip top and not bottom? It's to do with what the original equation is asking for, Roper. So if you go from if the question specifically wants V3 to VO2 plus, you're not gonna change this. Okay, you're gonna keep this the same. Did biodiesel come up in paper 2 or no? To be honest, it's gonna, if it comes up, it's gonna be a multiple choice. I don't see it coming up as a main. It didn't come up. Really, it didn't come up. Ooh, that's very interesting. Okay, all right, okay. That is actually a topic to get down. All right, I will make a note of that. Let me just write that down here. If it comes up, it's a multiple choice, so I can guarantee. All right. Draw the structure of the nucleotide that contains guanine, showing the bonds. Okay, let me get you guys the formula book. Give me a moment. 1 second, guys. Formula book. A level. This is not for OCR, by the way. This is only AQA. This is only AQA. It's not OCR. So if you guys are OCR students, just sit back for a bit. Okay. 1 second, guys. All right. Here we go. That is your data. Now, to be honest, I haven't seen this in a while. I can imagine this coming up. Yeah, I do. We will. No amines or base strength. Really, no amines. Really? That's surprising. I can imagine then a question will be like, what's the amine produced from excess of blah 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 with thingy. Hey, NMR, yeah, NMR, there will be maybe like how many peaks there are, or splitting or something like that. Amines is surprising though. That's really surprising. I think it'll pop up 100% and then multiple choice, so there'll be at least 2 questions on there. But DNA is popping up, man. DNA is 100% popping up in some way or form. It hasn't been examined in ages. No. DNA is light. Trust me, it's light. It's light. Okay. First thing, what you're gonna do, right, is This is the first thing you're gonna do. Okay. Sugar, pentose, and base. Draw this little diagram. You need to memorize this. Okay. You probably already know. If you guys do biology, you probably already know this. Okay. I know. Okay. Now, you can see that this is your phosphate group here. So what you're actually going to do is the parts from the phosphate that are actually going to attach is actually your OHs. Okay, that's specifically what's actually going to attach. And essentially you can kind of copy this across if you really want. But this is how I'm going to draw this, okay? P, double bond O, single with that. And then what I'm going to do is actually a single bond O on the top and a single bond O on the bottom. Okay, why? Because these are your phosphodiester bonds. That attaches to your top one, and that attaches to your bottom. Okay, and technically you actually have the second phosphate binding from there, which kind of looks like this. Okay, if you want to get that down, that's up to you. That's essentially your phosphodiester bonds in terms of how the DNA interacts with each other, or nucleotides interact with each other. Okay, but this kind of diagram you need to know. You can use it for your condensation essay. Alright, next what we're going to do is we're going to use deoxyribose. Okay, we're not going to use glucose. This never comes up. This probably not coming up. You're going to be using deoxyribose. Okay, essentially copy this entire diagram. You can draw it in structure or skeletal if you really want to. But again, you're thinking about condensation bonds. Okay, look at your diagram. Okay, your diagram has a bond here, your diagram has a bond here and here. Okay, and you can see we have 3 OHs where we are going to make our bonds. Okay, what bonds to the orange lines? Good question, Jeremy. Essentially your deoxyribose. Okay, now we'll use the bottom orange line, which we're going to use to bind to the deoxyribose. Where's my mouse gone? Oh, my sensitivity is really low. Okay, there we go. Okay, so what I'm going to do is take this deoxyribose. Let me actually make this a bit more bigger so you guys can see. In fact, let me take a screenshot of this deoxyribose. Give me 1 second. And I'm going to take a screenshot of guanine as well. One moment, guys. One moment. Just so you guys can see a bit more better. Copy, paste. And also, it was guanine. There we go. All right. We'll look at guanine in a second. Now, deoxyribose, you can see we have an OH here, OH there, and a hydroxide group there. So what I'm going to do, because we're trying to make a condensation bond, essentially what happens is, you probably shouldn't do a bond like that. I'm going to draw a bond like this, okay, and it attaches to the CH2. Okay, it attaches to the CH2, which therefore makes the rest of your bond. I'm going to keep it as OH for now, like so. Cool? Is that calm? That's not calm. There we go. Where I get the P from, that's your phosphate group. That's going to be given to you here. Okay, that's your phosphate group. You're going to be attaching the tops and the bottoms. Wherever you have an OH, that's essentially where you're joining up. Thank you, bro. Thank you, Yam. It's beautiful. It's beautiful. It's beautiful. And let me draw it again. That's actually horrendous. It's horrendously ugly, man. You know what? Let's do it in skeletal. Why not? Let's do it in skeletal. Boom, boom, boom. There we go. Alright. Calm. Now, actually, let me make this a bit more better. There we go. Now, this part on the bottom will essentially, we don't need to draw this right now. Just say showing clearly the bonding between the components. We can if we need to, but in this case, we won't really get the mark. But essentially, we will attach another phosphate. Why wouldn't we take away the H's? What do you mean? We would take away the H here. We would. Okay. And to be fair, if you really want, you can draw a bond like so. Okay. You can draw a separate bond out like that. Anywhere that has a hydroxide, chances are you'll probably be making a condensation reaction bond. Now, this thing, guanine. Guanine is in this case what we're attaching on. Now all your bases actually, if you're ever forgetting where you're actually going to attach, if you look at where you have an NH that's vertical, okay, remember the vertical region of your base is essentially where you're going to be attaching your ribose to that base. Okay, no, don't leave Ava, no, don't leave the H in, just because we're going to be attaching to our guanine, that's why. Okay, so we need to somehow essentially take this guanine and put this there. And actually I should probably take out the OH completely, just because if I have an OH here and I have a H here, this is my condensation bond. What does it make? Water. So I'm going to take that OH out and that H also come out. Now what you can do, okay, this might make this a bit more easier for you. In your exam, flip your formula book around. Okay, flip it completely around. And I'm literally going to do that as well here. Flip vertical. And it will look something like so. In this case, I can't lie, it does not help you at all, bro. I'm gonna be real. But in some cases, it will help you. Okay. If you want, what you can do actually is you can trace it. I don't know how you're going to trace it if you don't have tracing paper, but draw it on a separate piece of paper or in your formula book as well. That also works. Actually, don't do that because I know they like to copy it across. Unless you get a sheet. I think you get a separate sheet, right, for AQA. Anyways, what I'm saying is make just trace it. Just trace it. Draw it like it. Draw it like this, isn't it? Okay, make kind of like a mirror image, and either this way is going to be helpful, or turning around your page will be helpful. Okay, it doesn't have to be amazing. Okay, all it just needs is the right amount of bonds, and you should be fine. Okay, this NH that goes down, and again, doing it in pencil will always help you. That should be an N in between. That should be there. There should be a double bond there. There should be a double bond there. NH2 there, and you can see that's more or less a reflection. Okay, and originally there was an NH there, but since we are attaching this base, okay, since we're attaching the base onto our ribose, what I'm going to do is actually get rid of this H like so, and that is a question done. Okay, that is our guanine attached to our DNA. Does that make sense? Yes, Bean. Does that make sense how I've done that? There shouldn't be a bond there, by the way. Okay. Kind of put a line in between, make it a mirror image. Or, turn your formula book around. Do it like that. And remember, anything that has an OH, chances are you're going to be making a bond. Okay, so your hydroxide, if you're ever working with glucose, if they actually do give you glucose, for whatever reason, those are going to be your bonds. OH on top should be always O. You are not connected. If it's not connected, it's the OH. Okay, but if it is connected, this will be connected to essentially your next phosphate group, which is from the bottom. So you'll have a phosphate group like so. Okay, that's essentially what the next group is. So you essentially have another nucleotide, and this is essentially going to be a phosphodiester bond. So this is one diester bond, and this is another. One phosphoester bond, and this is another phosphoester bond. So you end up with your phosphodiester bonds. Does that make sense? Okay. Now, in terms of your bases making hydrogen bonds, just about to answer that, Young. So remember this: adenine and thymine make 2 hydrogen bonds, and cytosine and guanine make 3 hydrogen bonds. And this kind of looks like triplets. Really, they're not. Or triple bonds. They're 2 hydrogen bonds and 3 hydrogen bonds. If you're drawing a section of DNA, do you put the O, H in, or do you extend the... It's better to extend the bond. It's better to, I'd say. You won't lose the mark. You most likely won't. If it says a single nucleotide, in here it says draw the structure of a nucleotide that contains guanine, showing clearly the bonding between the components. You should be fine, but I'd say it's just better to. Okay. Just remember that your OH is you're trying to make a water. Okay, so if you're ever unsure, is there an O here, is there an N here? Just think about how can I make a water. Okay, that will be your best friend. Okay, next question essentially is this. Adenine and thymine make 2 bases. Cytosine and guanine make 3 bases. This is your question. This is your formula book. Attempt the question. If you want to trace it on from screen with the original question, go for it. I'll give you guys a couple of minutes. I'm gonna read off TikTok chat if they are asking me anything. Isaac, I did not. I did actually. You're right. I did. Oh, you're right. It should be. It should be like that. You're absolutely right, Isaac. Isaac, you're absolutely right. There should be a CH2 there. But yeah, this still carries the same way though. All right. Draw multiples. Now you're not expected to do multiples. But to be honest, if they actually do tell you, because I've never seen glucose. 3 marks, bro. 3 marks. I've never seen glucose used. I've actually never ever seen the hemoglobin also used. Never seen it used. Okay. Give a trace off the screen, and then I'll give you guys like a minute or two, and then I'll start kind of behind you. You're gonna skip it? Nah, I can't lie. It's good marks, bro. It's good marks. It's really good marks. Okay, well, this is at the moment, you guys. But let's see what type of base this is at the moment. Let's compare it with what we've got. Well, this is only double O with one double O there, and maybe this. There's an NH. Oh, sorry. There is no CH3, so I'm gonna assume that this is a cytosine. It's not actually. No, it's not. I take that back. It's a guanine. Okay. Well, guanine we know makes 3 hydrogen bonds with cytosine. Okay. This is gonna be a complementary base to guanine. Now, this will be helpful. Let me take a screenshot of cytosine. So you should have identified that cytosine is going to be your complementary base. Let me take a screenshot of this so you can just make it a bit more easier. And this is what you're going to do in your exam. Maybe RJ, maybe you're right. I heard that there was a lot of biochemistry, potentially cyclic areas. Huh? Yeah. 2 cyclic areas. It's because of this, no? Unless I'm wrong. Oops, sorry. It's because there is no CH3. Okay, in our groups here, there's no CH3, so it cannot be thymine. Okay, we know that there's a double bond O here, so it cannot be adenine. Okay, well, it has to be one of these. You know, there's 2 rings here. There's no 2 rings here, so it cannot be cytosine. Therefore, it's guanine. RJ, wait, man. We'll get that after this, okay? Alright, so that means that if this is guanine, our complementary base, it has to be cytosine. Okay, now we need to figure out how the hell do we actually do hydrogen bonds between them. Nels, no, I have not gone over rates yet, no. Okay. Again, this is going to be my hint. Flip over the page. RS maybe 10-15 minutes ago. Yeah, but we did chromatography at the end of paper 2. I'll go over it again though, because I didn't go over it in much detail. I skipped over it quite a bit. I went over it really brief. But I think it's 100% going to pop on paper 3 though, in somewhere. What I'm going to do is flip this potentially upside down, maybe. Let me just look at this. Oh, we don't need to. We actually don't need to. Organic liquid thing. What's organic liquid thing, bro? What's organic liquid? Am I tripping? What's organic liquid, bro? Yeah, we're gonna reflect it, yeah. So if we go ahead and reflect this, the reason why we're gonna go ahead and reflect this is because where we make our hydrogen bonds from guanine, it's actually a good idea to kind of learn where your hydrogen bonds are made, because sometimes it's a bit hard. But in terms of guanine, it's actually pretty easy. Guanine and cytosine, you can see that this area here is kind of like a puzzle piece to this area here, so they kind of like join together. So the guanine and cytosine, they will have the hydrogen bonds between there. In terms of adenine and thymine, they're going to make 2, and usually you're going to make your bonds between you're going to be making some bonds between your double O oxygen. Again, try to use it as pieces. In this case, where is a bond going to be made? This and the NH2, and here the H and the N. That's where your 2 bonds are going to be made. Okay, this one's a bit more trickier to kind of flip around, but this one's a good one. AQA on site, yeah. I really, really want to see the papers myself, bro. Um, you know, I'm gonna. I know people have said that some people say that AQA is easier than OCR. I completely disagree. I think AQA is harder than OCR, and that's respective in terms of the grade boundaries. You can see that. No offense to the OCR brothers, but yeah. Okay, I'm gonna flip this across, so this becomes the following. I'm gonna make a benzene ring. Um, like so. N. AQA is easy. Nah. I'm good, Ali. Ali, I'm good, bro. I'm good. I'm good. I've sat my chemistry, bro. I've sat. I'm finished now. Boom, boom, and there should be a double bond O there. Cool. And then if I just move this across, you can see that this actually lines up very, very nicely. I'm going to draw the NH2 out separately, so this becomes N, H, and H. And you can see that I'm going to make a hydrogen bond there. Make sure it's in dotted lines. Okay, hydrogen bonds between H and N, and hydrogen bonds between your O and your H as well. Okay. A good thing to remember is that the only place you make hydrogen bonds is between F, your fluorine, your oxygen, and your nitrogen. Okay, and technically there should be some sort of that should be fine. Even that you should get full marks for that actually. But if you did decide to put a very very similar diagram like this, that's also fine. Fiver, yeah. It doesn't have to be horizontal, no. It doesn't have to be. As long as it's a dotted line, Jeremy, that's fine. Yeah, dotted line is the main thing, and the right. Oh yeah, you're right about the lone pairs actually. There should be some lone pairs between nitrogen like so, specifically for this nitrogen bit, and for the oxygen. There's not really lone pair for oxygen. I mean, technically there is. But the key bit is your atoms there. I'm gonna be honest. For 3 bags. Jacob, it depends on the question. If they do ask, it's gonna be nitrogen's gonna have your lone pairs. Okay, and your oxygen's gonna have your lone pairs. Okay. But you don't need to normally. What was that? Was that an N? That was an N, I think. When is break? You want break already, bro? It's only been 2 hours. It's only 2 hours, bro. Alright, let's have a quick break then. Go on. Let's have a quick break at 7. We'll come back at 7:35. Yeah. Yo, that might be alright, Shah. Yo, young, we've done 5 hours straight before, man. We've done 5 hours straight. Yeah. Come back at 7:35. Yo, I see Neil. Yeah, Neil. He does 12-hour streams, bro. Crazy guy, man. Crazy guy. You know, I respect though. Yeah, do some multiple choice questions. What did I do? What did I do in the first hour? I cannot even remember, bro. I'm gonna be real. We did some electrodes. We did some heterogeneous. We did some KP. We did some pH curves. Autocatalyst equations. Yeah. 9 a.m. to 9 p.m. is crazy, bro. Did he have breaks? I heard he was bugging out. I read someone saying in my Discord. Constant stream till the exam starts. Damn. To be fair, my sleep schedule is pretty broken. I find out I sleep late these days anyway. Alright, boys. I'll be back in like 5. We'll restart at 7:35. Yeah. Nah, we're not doing until 9, bro. We're doing cookie at the end, fair. Yeah, I think I've seen that. Alright, I'm gonna be back, guys. voice. You went sick. One second, one second. I'm just looking at 10B. Guys, 10B is just distillation, bro. Do you guys want to go over that? Could you just make an essay? It's just distillation. If you want me to go over that, I can. I mean, but to be honest, it's just I mean, there's isolation using your separating funnel. Other than that, it's not really much in terms of that. Aqueous layer 1. Oh, sorry, you can't see me. It's my bad. My bad. What do you mean aqueous layer? Am I tripping? Sure. Which one? In terms of the separating funnel. Chill out, guys. Chill out. 8:30 maybe. I've heard about it. I wish I did see it, but I've not seen the. I've not seen it, to be honest. I've seen unnecessary, like, not unnecessary, unofficial. I don't know why I said unnecessary. Unofficial mastering I've seen. Amazing. I appreciate it, Ibrahim. All right, you know what? Let's start with some chromatography. When we queuing Val, yo, chill out, bro. I'm so shit. I'm gonna be real, man. I'm so ass. Yo, I can't do that in 1 hour, man. I'm gonna be real. I could do it in like when I was doing my real exam, chemistry. I could do it in like 1:30. But you know what it is? When you're explaining at the same time, it doubles the time. At least it doubles the time. Like when I was recording my 2023 from mechanic and stats past papers. Like they're not bad, to be honest, but it's more or less the two tests combined together. They add up to 1:55, 1 hour 55 in terms of video. It's just going through in terms of detail. Anyways, have a read of this question, guys. For the guys on TikTok, my bad, you guys can hear screaming in the back. This is AQA, but it can be 100% transferable to OCR. Yeah, and honestly, I can say that you can say that for a lot of the exams, like maths. It's really peak, but I heard maths stats 3 was really good. Paper 3 was good. You're carrying me, yeah. You're gold. Yeah, I used to be like silver, bro. I was so ass. My aim is not even bad. You know what it is in Valorant, yeah? It's the mechanics, bro. As soon as you move, the bullets just doesn't hit. And I peek and I'm just headshot it straight away, man. Let me see that shot. Let me see that. Guys, if you haven't already, just join my Discord. I'm always lurking about. Yeah. That's separating funnel. Yeah. Yeah, I'll go over that. I went over this in, I want to say paper 2 briefly, very brief. I'll go over that. Yeah, cool. That's calm. And biodiesel as well. I need to make a note of that. I'll keep that on the side. My bad for the screaming in the back. Can't really do much about it. Just gonna deal with it, guys, on TikTok. But biodiesel and separating funnel. I'll go over this. Like 4, bro. Like 4. I'm gonna be real, man. All right. Bottle was discovered. Okay. Was labeled propan-2-ol. A chemist showed using infrared spectroscopy that propan-2-ol was contaminated with propanone. Okay, so we have 2 different molecules, and it's column chromatography. Okay, as soon maybe sure. Can you hear it? I think it's a bit better on my YouTube stream though. I think it's a bit better on my YouTube stream just because it's a bit suppressed, but it still might be able to hear it still. Anyways, as soon as you see chromatography, what you want to do is separate as much of your molecule out into polar and non-polar. And that's going to help you a lot. But in terms of propan-2-ol, well, propan-2-ol is definitely polar. Whereas propanone, well, because we have propanone that looks like this, okay, with a double bond O, because of the symmetry, the polarities get cancelled out. And what happens is this becomes a non-polar, or you can say less polar molecule. Okay, not necessarily non-polar, but I should say less polar. This one's column chromatography. You know I'm muting this, bro. I'm closing my window, bro. It's actually they're screaming for no reason, taking the piss, bro. They're literally screaming for no reason. What they doing? It's spoiling though. I need that window open. No, chill out, bro. Yeah, okay, chill out. My biceps ain't that big, bro. My real man. My triceps are better, bro. I ain't flexing though. Okay, let's continue on. The column contained silica gel, a polar stationary phase. Okay, I ain't got no arms. You're trying to bait me, bro. Trying to bait me. Chill out, Za. Chill out, bro. Come to YouTube. Come YouTube, man. And then, cool. Now, I'll probably draw a diagram. I think it's good to draw a diagram. Now, since this is silica, which is polar, right? That means that propan-2-ol, which is polar as well, is gonna be more have affinity. Propan-2-ol will have more affinity towards your stationary phase. Okay, this is your column chromatography. Good. Then, contaminated propan-2-ol was dissolved in hexane. Okay, so it's dissolved in hexane. Hexane is a non-polar molecule, which means that propanone is going to have more affinity to hexane. Propanone has more affinity to hexane, which is your mobile phase. Sorry for the bad handwriting. I'll clean this up. More affinity to hexane. Alright, cool. That means that it says pure hexane was added slowly to the top of the column. Samples of the eluent, the solution leaving the bottom, were collected. Suggested chemical process that would cause a sample of propan-2-ol to be contaminated with propanone. We'll worry about that later on. This is the key bit though. Suggests why propanone were present in samples of the eluents collected first, whereas samples of containing propan-2-ol were collected later on. So this is essentially the reason, because your propanone has more affinity to hexane, which is your mobile phase, okay, whereas your propan-2-ol, okay, remains up, okay, remains with silica, so it takes longer to come down, okay, and this is a good way to essentially separate. Why is propanone mobile phase good, Mikhail? Good question. Essentially, propanone is non-polar, hexane is non-polar. Okay, propan-2-ol is polar, silica, which is your stationary phase here, is polar. Okay, that's why. That's essentially your 1-2 marks here done. Like this is essentially your column chromatography. Now gifts are not on. I can't turn it on. It's you can do it through the description if you really want to, bro. You don't have to, or don't. Like, you guys being here is more than enough. But I need to have, like, I think it's 4,000 hours. I think I was checking it the other day. Shit. Yeah, I'll go over it again, yeah. Okay, essentially, let me go over this again. Give me a second. So, column chromatography. You have two phases. All your chromatographies, you have two phases. You have your stationary phase, and you also have your mobile phase. Cool. Now, what happens after this? That is that we've got our two samples, or two elements, or two compounds even, I should say. You have propan-2-ol and you have propanone. Well, propanone, we need to identify whether these are polar or non-polar. Propan-2-ol is a polar molecule, and propanone is a non-polar molecule. Cool. Now we need to identify the polarities of our stationary phase and our mobile phase. Well, your stationary phase, at the moment, is told us as silica. Well, silica is polar. So what matches? Your polar and your polar will be matches. Okay, it will be matching. So that means that propan-2-ol will have affinity with your stationary phase. That means it will tend to remain up. Good, BMZ, exactly that. Okay. Whereas propanone, since propanone, it does have a double bond O there. Okay, but because of your symmetry between it, essentially what happens is the polarities end up cancelling out. Can't see that. The polarities end up cancelling out. Therefore, this becomes a non-polar molecule. Okay, and well, we need to check what is our mobile phase. Well, your mobile phase is actually hexane, which is also non-polar. Okay, therefore, these two will like each other, and these two will like each other. Okay, stationary phase means it retains up. Okay, it's retained up here, whereas your mobile phase, it will drop down as your element. Okay, all your mobile phases, all your chromatographies have mobile phase and stationary phase. You just need to determine what is your polarities. Okay, why don't polar and polar repel? That's a very good question, actually. That's a really, really good question. That is a really good question. It's not the same thing as plus and minus, right? Yeah, that's probably the best answer. RS said that it's because they form hydrogen bonds. So mobile phases, they don't really form hydrogen bonds. So you just have like simple molecules like so. Like there's nothing that forms a hydrogen bond. You can kind of think of it in terms of like hydrophobic and hydrophilic. Your hydrophilic, if you do biology. Hydrophilic like attracts water. Why? Because it makes hydrogen bonds. Whereas hydrophobic doesn't like water. Why? Because it can't make that. Polar doesn't necessarily mean reactive. I mean, technically, I can see why you're saying that. It's just more tending towards making hydrogen bonds. Okay. The reason why it's 4 marks. This is just 2 mark stuff, by the way. This is 2 marks. The other 2 marks come from up here. Infrared spectrum of propanone. Well, that's going to be COO, and you just pull that out from the formula book. And suggest a chemical process that would cause a sample of propan-2-ol to be contaminated with propanone. Or because it says this, because it's dissolved in pod. Okay. If you're dissolving and pouring, that will be your mobile phase. That is the mobile phase, essentially. Okay, but generally you have 4 different things. Okay, you have 4 different compounds. My bad. You have 2 compounds, which are essentially what you're testing for. So your propan and propan-2-ol, and 2, which is going to be your stationary phase and your mobile phase. Okay, if it doesn't say this, if it gives you stationary phase, and you've identified the other 3, essentially, what you're left with, it must be the mobile phase. Nah, okay, no. Depends. If they ask, then do that. But it's really for you to figure out. That's essentially what's the whole point of chromatography. You have to identify which is the stationary phase and the mobile phase. And the first point is essentially, well, actually, you tell me, Ibrahim. You tell me. What causes a propan-2-ol to become contaminated with propanone? Or what chemical process would? You tell me, man. Think about testing. I think this is the way it's phrased. Think about testing. You tell me? You tell me? Yes, Archie, nice. Oxidation. Oxidation with what? With what? Specifically what? Give me reagents. Potentially, yeah. So yeah, exactly. The to be fair, the answer is just oxidizing, but absolutely right. When you do oxidize it normally in a chemical test, anyways, acidified potassium dichromate. Okay, amazing, cool. Ethan, amazing, cool. Perfect. The second point, it just says explain how the infrared spectrum showed the presence of propanone. You're just essentially going to say there's going to be a COO peak. Okay, and then I don't exactly know where the number is off the top of my head. I think it's like 1,650 centimeters to the -1, something like that. You just pull that out from the formula book. And you just write that down. Okay, IR spec. Okay, let me actually check. It is 1,680. I was pretty close. 1,680 to 1,750. Nice, yeah. Cool. So you just say that. Yeah, that's for ketone. Yeah, easy marks. Easy. Okay, cool. Next, some gas chromatography. Here we go. Yes. Do you want to go back up? There you go. There you go, Farah. For condensers and stuff, was it water? Yes. Yes, Ibrahim, yeah. Always in from the bottom. Think about it in terms of gravity, right? If you have a condenser, okay, and it's always going to come from the top. If it's coming from the top, then what happens is water will actually just fall straight down. Okay, so that's kind of like gravity. Whereas if you fill it up from the bottom, it has to fill up everything. I'm just trying to draw a nice looking condenser. There we go. Kind of. That's horrendous. There we go. That'll do. Okay, in from the bottom. How do you know that propane 2-ol is polar? Essentially, it's an alcohol, right? Any sort of alcohol generally is polar. So yeah. Do you want the annotated version, Tiber? I can do. It'll be a long looking PDF. It won't be very nice looking, to be honest. The video is recorded anyways afterwards. So yeah. All right. This is going to be your gas chromatography. Have a go at what you can do with this. If you want to start to do question 1, question 2, just say in the chat. Does the less polar one always have more affinity to the mobile phase? Not necessarily mobile phase, okay? It has more affinity to the more polar thing, okay? Because the stationary phase is polar, and propane 2-ol is polar, that's why there's the same affinity. Whereas mobile phase is non-polar, this molecule is non-polar, that's why it has more affinity. Okay, not necessarily mobile and stationary phase. It's to do with the polarities. Actually, after this one, we're going to be doing the iodine stuff, and then the separating funnel, and then specific heat capacity one, and then biodiesel maybe, and then some multiple choice, depending on time. State the meaning of retention time. What does that mean? Oh, I forgot to go over this dehydration one. We'll go with dehydration mechanism. It'll be like 2 minutes, to be fair. Field trip, yes, good idea, Bryn. Good idea. Let's go to AQA headquarters. What even is it? Is it in London? Yeah, we might not finish at 8:30, but that's alright. It's alright. We'll push it a bit forward. I don't mind. What's my predictions? Good question, man. Good question. Chromatography, I think 100%. Iodine test, or it'll be specific heat capacity. I don't think amino acids much stuff will come up too much. Maybe a multiple choice, maybe due to ions, or like high pH or low pH. We went over that in paper 2. How long substance spent absorbed to, or is it adsorbed? Don't use adsorbed there. Adsorbed is in terms of heterogeneous catalyst. Okay. In terms of gas chromatography, this is the exact term you need. That's what I'm thinking as well, Clips. Okay, this is the exact sentence you're going to need. The time taken, I'm going to spell time taken for a compound to travel through the coil tube. If you came on the paper 2 session and you stayed till the end, essentially the way it works, if you have a sample dissolved in gas, usually it's going to be inert gas, okay, and then you have a tube, a coil tube, and then it goes into your computer, which is your detector. Okay, this is essentially your retention time, how long it stays in here. You know, fair enough, actually, fair. You know what, that does work. It does work. Adsorber essentially means it's binded. In terms of gas chromatography, though, because specifically gas chromatography is talking about retention time, and it's the only place where it talks about retention time, you want to try and make it specific to it, because that kind of phrase is kind of generic to every single type of chromatography. For gas chromatography, you want to talk about the compound staying in the coil tube. Mobile is going to be your gas. Tube is fine. Tube is fine. You don't have to say coil tube. Your mobile phase, essentially, you know what, let me quickly go over chromatography for gas chromatography, if you guys didn't miss it. But, okay, essentially what you have is a sample. Okay, and this sample is dissolved in a gas. Okay, it can be nitrogen, it usually is argon. Okay, and Probably is going to be non-polar, but if they do give you a gas that is polar, for whatever reason, it shouldn't really be a gas that's polar. Most gases will be non-polar, but they use an inert gas. Now, because if your mobile phase is polar, sorry, non-polar, that means your coiled phase is probably going to be polar. Again, this all depends on the question as well. Sometimes it could give you different substances to use. Okay, but usually within this, there'll be some sort of oils or there will be some sort of compound that will allow the retention phase, or I should say the stationary phase. Now, when this goes through, essentially, if the solution polar equals polar mobile phase, yeah, exactly, yeah. Yes, RS, yeah. Actually, I'm gonna say no. I'm gonna say no to that. It's because you're kind of testing the fact that, okay, is my gas polar or is my gas non-polar? That's what you're essentially testing. That's the whole point of the sample. Okay, yeah, of course, one more time. So, sample dissolved in some sort of inert gas. Okay, usually it's inert. Doesn't have to be, but usually it is. Okay, and argon is a good one. Okay, then what happens is it's passed through the coil, and within the coil you have some sort of oils or there's some sort of compounds. Okay, don't worry about the polarity too much. Okay, I would try to avoid learning the polarities. Just learn that there's a gas and it goes through. Okay, your stationary phase is going to be in this coil. Your mobile phase is going to be is the gas that is dissolved in the first place. Okay, and how quick it goes through, essentially, it determines your retention time. So the longer, if it takes longer to come out, if you have a peak right at the end, if it takes really long to come out, that means it's going to have a high affinity to which phase? If it takes really long to come out, high affinity to your mobile phase or high affinity to your stationary phase? It's a gas chromatography, by the way. Good. It is going to be stationary. Okay, because it took really, really long to come out. Okay, whereas if it took really quick, if it was really quick to come out, then that would be your mobile. Okay, that's essentially your gas chromatography. Again, it's to do with your polarities. Okay, if it really likes a stationary phase, if it really likes it, it's going to stay. Okay, and they'll give you the compounds. Essentially, you're going to figure out whether it's polar or non-polar. The whole idea of chromatography is your polarities. Okay, and I used to find chromatography really, really hard with this idea of mobile phase and stationary phase. The key bit is your polarities. Okay, two of the compounds are present in the mixture in equal amounts. Explain how figure 2 shows this. Well, you can see you have different retention times, right? But essentially, the amount of it, you can kind of think, if you do maths, it's kind of to do with your probably, yeah, essentially, essentially, yeah. But the areas underneath the graph represent your, don't say height. Ooh, don't say height, say area. Say area underneath the graph. Okay, I know why you guys are saying height. I know exactly why you're saying height, but say area. Okay, area under the peaks are the same. If you did say height, I mean, you might get it, because what happens is sometimes you can have the same height as this, but the peak could be like this. Like the peak could be really, really thin. So that's why it's key to say area, because it just takes account of the fact that you could have a really small amount but still have the same detector response. Yeah, I mean, if it's assumed to be proportional, then yeah, HM, yeah. Okay, let's say area though. I would rather you guys say area. Okay, you guys want me to explain again? Sure. There's a sample dissolved in gas. Gas is your mobile phase. Oils or some sort of compound in this coiled, and this is going to be your stationary phase. Okay, we don't know what the compound is. RJ, listen up here. This is for you. If it takes long to come out, it likes stationary. If it takes quick to come out, it likes mobile. I think doing this question as well will explain a bit more as well. Okay, I think it's good to have some sort of application, because I think it helps with the understanding of it. Okay, give a reason why nitrogen is used rather than oxygen as the carrier gas. Well, okay, oxygen is non-polar. Nitrogen is non-polar. Why do we use nitrogen instead of oxygen? Well, to be fair, oxygen is technically... Okay, good. Nitrogen's inert. Perfect. So nitrogen is inert. It doesn't react with any of our compounds that we have here. Okay, whereas oxygen, it might go ahead and oxidize something. It might just go ahead and react. But nitrogen is going to be in it. RJ, which part? Which part are you talking about? Give me specifics. Give me more specifics. I want you guys to try question 4. Think polarities. Okay, do you understand the mobile phase and the stationary phase or not? do you understand the mobile phase? Okay, alright, that's calm, innit? Okay, do you understand that if it comes out quick, if the thing comes out quick, it means that it has a small retention time. And if it takes ages to come out, it's gonna have a big retention time. No, I'm talking about RJ, bro. It's RJ. Okay, someone said carbon dioxide for the question. Okay, do we agree? Do we disagree? Question 4. Alright, calm. Then that's it, bro. That's it. That's it. What else is there, bro? RJ, that's it. Okay, we got argon, we got aluminium oxide, and we got carbon. We got all 3. Alright. Polyethane 1,2-diol, PEG, is a liquid and is part of the stationary phase. Retention just means how long it takes to come out. Okay. Well, if the stationary phase, or if the mobile phase, let's go back to this diagram here. Well, now we've got some compound names. Our mobile phase is nitrogen, okay, and it says PEG, which is a diol. PEG is a diol, is a stationary phase. What is the polarity of PEG? What is the polarity of PEG? Is it PEG? Is PEG non-polar or polar? It's a diol. Good. It's polar. So if it's polar, that means within the stationary phase, we can only have polar things. So out of these, it's asking you which molecule out of these is polar. We can already cancel one off. Argon. Argon is an inert gas. Cannot be polar. Carbon and argon is a gas as well. We don't want gas in our stationary phase. In gas chromatography, usually I can't lie, it's gonna be stationary. I'm not gonna lie, Amma, but it all depends on the molecule. Carbon dioxide is symmetrical, so your polarities cancel out. It is a non-polar molecule. So the only one we have left is aluminium oxide. Okay, does that make sense? Yes, exactly, Jeremy. Distinct polarities, okay? Avoid memorization. Is stationary phase polar? Is this polar? Just memorize, or even memorize, just learn that, I don't even learn, understand about polarities. Yeah. Understand, bro. Nah, you guys are cooking though. You guys are doing really, really well. Honestly, when I was in A level, I'm gonna be real. I sat my A level, not even doing gas chromatography, bro. I didn't even learn it. I'm gonna be real. that was so bad. I should have learned it, but yeah. A diol's not necessarily symmetrical though. Smite ghost. Nah, don't do that, bro. I don't even know how the skin looks like. Yes, Mikhail, yeah. It's not 12-hour stream, bro. Stream, I mean. It's not 12 hours. What? What do you mean, why? Why for what? Let me look at the skin, bro. Smite ghost. Maybe. Oh, that's a good skin, to be fair. That is actually a banging skin. You know what? Do it, Mo. Do it. If you got the what's the currency of Valbucks, bro? What's the currency, man? Okay. Yeah, I'm gonna go over some practical stuff in terms of why we shouldn't use any acyl chlorides. Okay, or instead, why not to use acyl chloride, or why to use ethanol chloride. Oh, sorry, not ethanol chloride. And hydrides. Okay. This is essentially going to be your practical stuff. This is very linked to your carboxylic acid topic technically. So, yep, good. Corrosive. Okay, corrosive, it produces HCl gas. Okay, so this is not it's not hydrochloric acid, but hydrogen chloride, which is a toxic, corrosive gas. Okay, it's good. This is cheaper, anhydrides are cheaper, or you can say your acyl chlorides are more expensive. I do have a list here. It's dangerous to use. Okay, and there is one more. It reacts violently. This is just why not to use acyl chloride. Yeah, vulnerable to hydrolysis is a really good one. I would argue that comes under expensive. Good RS, I like that for anhydrides. Okay, so essentially it's like the opposite for your anhydrides. But essentially this list is not why not used for acyl chlorides. Okay, and I'll do the other way. So this is cheap, I guess, easy to store. Okay, and yeah, like it's not corrosive. Yeah. Okay. Why to use anhydrides? Before you said propanol is non-polar due to symmetry. We don't ignore. So we don't ignore this, the CO. Yeah, essentially we ignore the CO basically. Yeah. Don't. I would advise not to ignore. That's not a good term. Think in terms of symmetry. Like the polarities they cancel out. That's the better term. Okay. Yes, Tanya. Yeah. Tanya, exactly. It can vary. It will always just tell you in the question though. Okay, HCN. Actually very, very similar. HCN is just toxic. Okay, so you should never ever use HCN. Okay, instead use KCN and hydrochloric acid, or it should be concentrated hydrochloric acid. Okay, this is toxic. This is really, really toxic. Okay, if it ever asks you for like the reason behind it. All right, let's go over the iodine experiment. And actually, I'm gonna pull up the 6th marker. This is, I can't tell you which is from. It's 2020, maybe 2020 paper 3, I think. So this is from a paper 3 though. Yeah, yes, Bryn. Yeah, don't do that. Okay. This came up, and I think it's a really, really good question to essentially memorize from Mark Scheme from 2020. Is it 2020, Hassan? Cool. But I think this honestly gives you all the ins and outs of iodine clock test. Yes, Shah. Is it the? Yo, Shah, what is that? What is that? I've deleted that, bro. Don't be sending pictures like that. Give me a horror, bro. What's my PC specs? It's not very good, guys. It's like very outdated. It's like a 1060 ROG Strix. I got 32 gigs of RAM though, DDR4. Ryzen 5 3600, I think. Yeah. I built it myself like back in year 10. I'm gonna be real. I've had this for like a while now. So it's like 4 years old now. Very, very old. I need to get a better PC though. When GTA 6 comes out, I can't lie, I need like minimum like 3000, 4000 series. Can't we talk about transition metals for E? No, because dark blue. But it does the job, bro. It does the job, man. It's a 6 gig. It's doing the job. Alright. Yeah, bro. Granny GTA 6 coming out next year though. Is it next year? Or is it 2027? I can't remember. Yo, guys, Squid Game is coming out on the 27th, boys. I might actually get a PS5 for that though. I don't play console. I'm so ass with the controller. And let me actually answer this question though while I'm talking. Okay, let me read this question. In the aqueous solution, A, B, C, and D are all colorless, but E is dark blue. The reason why we talk about don't use transition metal, it really depends. In this case, they haven't really given you any sort of like names or reagents, so this is what it is. But let's just talk in terms of like the letters that they've given us. Okay, and this actually transfers to all your iodine testing. It doesn't have to be necessarily with A, B, C, and D, or it doesn't have to be with iodine. It just depends on the actual question itself. Okay, first things first, always when you have a practical, and this is essentially asking you to write down the practical. I don't think really chemistry likes to do this too much, so it's quite down there on the way they like to ask questions. But anyways, first things first, you should always measure a certain amount of your reagents. Okay, so I'm going to say measure 10 centimeters. You just use some random volume. I just made 10 up. Okay, 10 centimeters cubed of A, B, and C in separate beakers or separate. I should probably say measuring cylinders. Okay, measuring cylinders. Okay, try to include apparatus within your synthesis. Okay, then what we're going to do is, because the question is also asking us a reagent X is available that reacts with E, essentially this is your indicator, you could say. Okay, so for example, starch goes ahead and reacts with iodine, or you can say a base kind of reacts with your phenolphthalein in some way. Or I should probably say, is it base or is it acid? I always forget. But you get the point, like there's always some sort of color change. Okay, so this reagent, we're also going to make some sort of measurement. So I'm actually what I'm going to put, because sometimes it can be an indicator, you should probably use a very small amount. So I'm actually going to put measure X with maybe a pipette. With a pipette. Or I should probably say 5 centimeter cube pipette. Try to give volumes on your apparatus. You just make it up, Ava. Just make it up. I can't lie. Just make it up. This is your iodine testing. Okay, this is your iodine clock test. Okay, in this case, it's generalized. It's a generalized. Okay, so essentially, I'll give you like a brief overview of what the iodine clock test is. You have a bunch of different reagents A, B, and C. Okay, you put them all. You put them all in, and as soon as you put this last one in as well, okay, make sure you have your indicator within here. What happens is you put on a timer. You put a timer on, and essentially you time how long does it take to essentially turn black. Okay, and then once you've done that, you record that time, and then if you go back up to the question here, you can see that we should really be changing the concentration of A. But yeah, so it depends on the order of which you're testing the order of. Let's say you're testing the order of C. Let's say you add C last. So what you do is change the concentration of one of the reagents. Let's use C. Okay, and then you do the whole test again, and then just do it with the timer until you get some sort of graph. Okay, and then what happens is, okay, you have different types of graph. Do you have a first order graph? Do you have a second order graph? Do you have a zero order graph? Yeah. Okay, yeah. So you have a rate against time. Rate against time graph. Okay. But anyways, we'll continue on the question. Essentially, this is your iodine testing, practical, in simple terms. But we'll continue on. In terms of indicator, again, this is generalized. Sometimes they'll always give you kind of context of what reagents you use. If they use iodine, then you probably will use starch. But it really depends. Okay, sometimes it could be universal indicator. We don't know. Okay, but since it says dark blue, you can just use X. Is it against concentration? One sec. Yeah, I don't know why I put time, because rate is 1/T. That doesn't make sense. Yeah, sorry. Yeah, you're right. Yeah, rate against concentration. Sorry, guys. Yeah, you're right. Yeah. Cool. You do have another type of graph, which is concentration against time. I don't really like those type of graphs. They come up more in OCR, because yeah, it's to do with your half-life and this kind of stuff. But it can still pop up technically, and I'll go over this, and I'll go over that in a second. Anyways, once we've measured our X and all our reagents, essentially, what we want to do, okay, we want to add specifically A last. Okay, you can technically do B or C, but it's probably better to do A, because that's the one we're going to be changing our concentration of. Do not add your X last. Okay, do not add your indicator last. Okay, so in a beaker, add B, C, and X. Then add A, and start the timer. Okay, you want to start the timer. As soon as you add A, you want to start the timer. Okay, then what we need to do is stop the timer as soon as, and always use the context of the question, as soon as the solution turns dark blue. And I'm going to kind of talk about the different potential errors of this as well. Turns dark blue. Because you're timing with a person, what happens is time can be one. There can be something to do with the reaction time of the person. So reaction time can affect your time as well, of human stopping time. Okay, and secondly, subjectivity. When is it that you decide that it's dark blue? Like you deciding on it's dark blue and another person deciding it's dark blue can be different. I don't know, like you might have heard this, like the red I'm seeing is probably not the same red that you're seeing. So how do I know that red is red, basically? Okay, so there's the levels of subjectivity of when reaction is complete, essentially. Okay, and that can essentially cause different results. And to go around this, essentially, what the potential fix of it is to use the same person every single time. Or you can use the idea of colorimetry, sorry, and you could potentially, I know it's a bit hard in terms of using the actual colorimeter because it takes so long, but if you use a potential computer with colorimetry, which, you know, detects it, that can help, you know, speed up some stuff, or in terms of like accuracy, because then you're using an actual numerical value without just saying, oh, this is opaque or it's dark blue. The colorimetry actually gives us a proper number that we can work with. Okay, and same with your reaction time, you can probably use some sort of computer to help you with that. For the method, can you use a gas syringe? Yeah, you could to measure. 100% you can use a syringe. I would avoid using the word gas, just use syringe. Okay, just use the word syringe. To measure out the reactants. I understand why he's asking that. Don't use the word gas, but you just say syringe. That works. Okay, let's continue on. At what point are we at? We've measured all the reagents. We've added the reagents. We stop the timer as soon as the solution turns dark blue. Okay, now what we're going to do is what are we going to do? 1 second. Let me go back to the question. We're going to record the time. That's what we're going to do. Record the time. Okay, and then what we're going to do is use the same concentration of B and C, but your A has to be different. And I would actually recommend that you probably just say add on by 0.1. So potentially even, I'd probably maybe add a concentration here. Let's say with 0.1 moles per decimeter cubed, and then I'm going to try it with maybe 0.2 moles per decimeter cubed. Okay, try to give as much as numerical value. Just make it up on the spot. Okay, and we should probably also be using the same volumes, just so it's a control variable. Okay, we should also be using the same temperatures. Okay, use same temperatures. How can we control temperature? Is there any way we can control temperature? Yeah, of course, Amitha. Yeah, of course. Calling me onk, bro. I'm not an onk. Good, water bath. Good, water bath. Can you link the concentration quantity of A to zero dilution? Yeah, you can. 100% you can. Good, water bath. With a water bath. Well done, guys. Okay, well, once we've done that, we're going to start the reaction again, essentially. Okay, with a different concentration. We've basically said that. And then once we've done that, when all data is observed, my camera turned off, my light turned off. Observed, what we're going to do is we're going to find out rate. How do we work out rate? 1 over time. Time taken. Okay, and we also will use that concentration. And I would actually recommend you just draw the graphs. If graph looks like this, specifically with rate and concentration, okay, that's order 1. This is order 0. Just draw the graphs. And this is order 2. Okay, there we go. Okay, that's going to be a full, more or less, 6 marks. I should probably say plot a graph here as well. Plot a graph with rate against concentration. Okay, I'll zoom out so you guys can get all of that. It's a bit hard to read, to be honest, but that's the diagram there. I'll make this a bit more bigger. Cool. If you want me to zoom in anywhere, just let me know. And yeah, there are 2 different versions. Yes, they are. So there's a rate and concentration graph, and there's a concentration and time graph. Yeah. Well, guys, you have, honestly, it's a little bit left. 1 exam left. Yes, Victor. Yeah. It's essentially your indicator, see. So your starch reacts with the iodine, and when that happens, essentially what you're doing is if you do biology, iodine tests for starch, and when it's there, essentially it just makes a dark blue color. Okay. If you what is the purpose of water bath? To the purpose is to control the temperature essentially. 14 hours. Allow 14. I said 14 hours. You guys said 12. I said 12 hours. I said 14. To change concentration. It doesn't, but because it says order of this reaction with respect to A, essentially you have to change the concentration. You have to change the concentration of A because it says order of reaction with respect to A. If it said order of reaction with respect to B, C, whatever, then you would change the concentration of that. That's why. Yeah, you should, Kay. You should. Am I going through multiple choice questions? Good question. Good question. There you go. If you want to get zoomed into the question, there you go, TP. All right. Do you have to use high concentration of B and C? Just keep it the same. Whatever it is, just keep. The main thing is keep their concentration the same throughout. If you're not testing against them. Okay, I'll show you the concentration graphs. For this is gonna be more OCR content, to be honest. I'm not going over half-lives. Sorry guys for OCR. That is a wrong graph actually. But you have your concentration and your time graphs. Okay, that is zero order for concentration time. This is order 1, like so. And then order 2 is actually very, very similar, but it's just more exponential, so it decreases more exponentially. Okay, so it has a steeper decrease. That's order 2 and that's order 1. That's the difference between them. Okay, these are concentration time graphs. Will it come up in AQA? Maybe. Will it come up in OCR? Probably. So yeah. I want to quickly go over dehydration and hydration mechanisms. And then, actually no, I promised Shad I was going to do separating funnels. So I'm actually going to do that first. Give me a second. Let me get the details up behind it. Separating funnel. I went over this in paper 2 though. Alright. First things first is when whenever you make some sort of organic solution, whether that's hexane, whether that's some sort of alcohol, it doesn't really matter. This is your separating funnel, and I think it's a really small bit of the spec in my opinion. It's a nice topic though. Yeah, go back. Alright, cool. Both can come up honestly. This is for AQA. This will probably be your more common one for AQA. Okay, concentration on the x-axis, rate on the y. Okay, but both can 100% come up. Yeah, come. Okay. Alright, cool. Now, separating funnel, you got this looking thing. Okay, and there's a tap. And essentially, it's all about with your densities. Okay, if you have a more dense liquid, it goes to the bottom of the separating funnel. If you have a lighter liquid, it's gonna go to the top. Oh, my OneNote's bugging now. Nice. Okay, this is your technically it's 10B, Mikhail, for AQA. Alright. So more dense liquid at bottom after you've made it. So this is, you add it in and you're trying to separate a mixture. So specifically you separate a mixture. Yeah, I mean that's also true, Bryn. Yeah, you're 100% right. You are right about that. But the key thing is because it's a mixture, they're immixable. Immixable solution I think is probably better. No, you're 100% right about that, Bryn. Immixable solution. Immixable solution. They might do a see. I feel like separating funnel is a very small bit. And essentially why they might ask immiscible. Immixable? Immiscible. Anyways. No, you're right, Bryn. You are right about that. I have seen that. Yes, Taiba, yes. So most of these going to be with your ester stuff. Ester, to make the ester, essentially is your distillation stuff. Immixable is just when your two solutions don't dissolve within each other. That's the best. So water and oil, for example, they're immixable. Im Immixable. Okay, let's continue on. Yeah. Yeah, the solutions don't mix together. Okay, but what happens is when you put them in the separating funnel, the more dense liquid goes to the bottom. So whenever you're talking about unmixable, yes, Ethan, yeah, more or less. That's like more or less, yeah. The more dense liquid goes to the bottom, and the way you take it out is just with your tap. You take it out. I'm a shush man, Thank you, bro. I love you too, man. And then you essentially pour that into a beaker. Okay, and then you end up with your blue. That's an airball. But yeah, so let's say you get your blue liquid out. Now what happens is a lot of the times when you make your esters and stuff, you actually have a lot of water in your solution that you take out. Sometimes as well, by the way, sometimes it's top solution that you need, so you just kind of get rid of the bottom. But that's for the sake of this. Let's say we need the bottom solution. Okay, so a lot of the times it has water in it, and what we essentially use in this, it's going to be your drying agents. We went over this in paper 2. Okay, okay, and then we're going to be using essentially calcium chloride. Okay, there are different drying agents. You don't have to necessarily use calcium chloride, but calcium chloride is a good one. And specifically, I will actually add in front of this anhydrous calcium chloride. It means just dry. And then once you've done that, essentially you've got your purified solution. And if you want to, you can go ahead and continue with more purification, more distillation if you really want to. Okay, but that's essentially your separation with a separating funnel. That's it. Yes, UV, yes. This is your drying agent. All right. Let's look at where is it? Dehydration script. Okay, not dehydration script. Dehydration mechanism. We went over this in paper 2. I'd avoid, by the way, avoid using magnesium hydroxide as a drying agent, just because it doesn't actually take all the water out. It's barely soluble, so not all of it technically turns into a precipitate. So I'd avoid using magnesium hydroxide. Okay. Dehydration, hydration. I don't know why. I just have a feeling something like this is gonna pop up in some way or form. Don't know why. So dehydration, essentially, you're going from an alcohol to an alkene, and essentially this is elimination. The mechanism name is elimination, and you also use H2SO4 as a catalyst. It's because of anhydrous. That's the main thing, RS. That's the whole reason why. All right, I'm gonna draw an alcohol on screen. Very simple alcohol. Okay, I want you guys to try the mechanism from what you can remember if you came from last lesson, or if you attended last lesson. How long has it been since you did the kid? Conditions, just H2SO4 already. You can say heat, but reflux, it's technically reflux as well. I'm gonna add reflux in there. But the main thing is H2SO4. Mechanism, I think it's in your multiple choice as possible. They'll be like, what's like the final products, or what's like the intermediate, or something like that. I think potentially. Everything we're doing here is gonna be on your multiple choice in some way or form, I think. And especially DNA and zooter ions. Okay, I'm gonna mention this again while you guys are doing this here. Zooter ions. Zooter ions have an overall charge of 0, by the way. Overall charge of 0. Okay, just remember this. Yeah, you can put concentrated. You can put concentrated. It doesn't really matter. It's just the whole purpose of this. Actually, what's the purpose of sulfuric acid? Inshallah, Muhammad. Inshallah. What's the purpose of sulfuric acid? Yeah, sure, Rahim. We'll do them. We'll do them in a bit. We'll do them after this. What's the purpose of sulfuric acid? Zooter ions. Yes, yes, yes. That's the whole purpose of it. Okay. Neither. It's a catalyst. Okay, cool. Alright. Let's do the mechanism of this, okay? Since it's a catalyst, H2SO4 is a catalyst, we're going to start with a H plus. Your lone pair is going to be on oxygen. Remember, negative to positive. Negative to positive. Okay, so your negative area is your lone pair, goes to H plus, and what happens is, your intermediate, you're going to make the following. And this is essentially very, very similar to your hydration mechanism that we did last time. But I'm going to separate this out as CH3. Okay, I'm going to redraw this as O. This time it has 3 bonds. Oxygen cannot have 3 bonds because it's in group 6. Therefore, you end up with a positive charge. Okay, we want to get rid of the water because we're trying to make an alkene. So what happens is, again, negative to positive. Your bond area is negative. It goes to the positive oxygen area. And then what happens is the water essentially pops off. And then we're left with the following. CH3. And I think they'll probably come up in your multiple choice. They'll probably ask you what's the intermediate or something like that. What's your final product? Okay, and then we try to make an alkene, so that's going to be your final, essentially, arrow, curly arrow. Okay, that's dehydration or elimination, you can call that. Okay, hydration is essentially the opposite way. If it does come up, I will quickly go over this. Okay, and then you can rewatch the live after. You're gonna start with H plus, negative to positive. Your double bond is an area of high electron density. That is crazy, Shah, but fairs. And then we're gonna do this. Okay, you're gonna attach the H basically anywhere, but if it's a major product, then it really depends. But in this case, you don't have to worry about major product or anything because it's just a H. Okay, and then we're gonna use water. Are we gonna use water? Are we gonna use water? Yes, we are gonna use water. Okay. Man, OneNote is being really slow today. Lone pair. This is a plus on the carbon because of 3 bonds. Curly arrow, negative to positive. Again, this follows the same way. This will learn negative to positive. It'll work with every single mechanism you do. Okay. As you can see, we cannot have 3 bonds on an oxygen. So again, negative to positive. The H plus comes off. That's your catalyst. Okay. Cool. I actually want to go over this mechanism real quick. This last one before we go over to the multiple choice questions. Yes, it's electrophilic. Yeah, it is. Yeah, it is. We just scroll up. All right, cool. There you go. Let me move this a bit more up. That's your hydration. That's your dehydration. Is that okay? All right. I want you guys to try this question. The second one is dehydration. Oh, sorry. No, this one's hydration. This one's dehydration. I should probably put it on top. Dehydration means get rid of water. Hydration means you add water. Okay, and the condition for it is steam and high pressure, but you don't really need to put high pressure, to be honest. Steam is fine. Steam or water is either fine, but specifically you do need your sulfuric acid again as your catalyst because that's where the H plus comes from. Electrophilic, good question, Mohammed. Electrophile, learn these terms, okay? Electrophile means specifically an electron pair acceptor. Okay, whereas a nucleophile means an electron pair donator. Okay, as you can see in this question here, we are going from negative to positive. This area of lone, this is a lone, it's not a lone to be fair, it's a double bond, which is a high electron density, but still the electron is going transferred towards the H plus. Therefore, this gets the electrons. Therefore, it's an electrophile. Concentrated. The only place where it's dilute is, I believe, your KCN and your dilute acid. That's the only place where you dilute acid. Everywhere else is concentrated. Correct me if I'm wrong though. Yeah. Only place to dilute is KCN. All right, I want you guys to try this question. I think it's really, really interesting. I think it's easier than it looks. Give it a try, and then we're going to look at some multiple choice questions. And yeah. Yeah. You're supposed to know it, bro. You're supposed to know it, man. Light work. I have not, honestly, bro. I'm gonna be real. I haven't. When your name is 2025 papers, bro, you gonna hook me up, yeah? Is that what you're saying? Is that what you're saying, yeah? Guys, if you can't do part A, you think about what part B is gonna be. What practicals do I think it's gonna come up? We went over iodine testing. Chromatography is coming up 110%. By the way, guys, if you are watch the paper 2 video, because today I didn't go over TLC. So I think TLC can still pop up essentially even with amino acids. And I'm actually gonna write this down. Your locating agent for amino acids in TLC is ninhydrin and UV light. Okay, so they could still potentially pop up. You want me to put prediction? Yeah, sure. Yeah, I'll put them at the end. TLC thin layer chromatography. So it's like, like the basic one, the one you do in GCSE with like the paper and like the little petri dish on top. I haven't gone over it today, but I did go over it in paper 2. I've marked it in terms of like the marked timings in paper 2 video. So yeah, both of them. So ninhydrin is like your locating agent, and then UV light you shine on it. No, you need both. You need both. No, am I tripping? Let me check. I'm gonna double check that. I might be wrong. Might be wrong there. Sorry, guys. And UV light. I swear it's together. Yes, it's together. Yeah, together. Together. Is it either one? I'm not an examiner, bro. I'm not. I wish I was. Can you learn? You potentially can. Yes, you can. You can use iodine. That is correct. That's completely fine. If it's either in fairs. That might be wrong there, bro. That's my bad. I used to use I2 paper. I used to use iodine as well. All right. Okay, this one is actually not as bad as you think it is. Yeah. For part A. Yes, for A. Yeah. Okay, so for part A, yeah, I'm just gonna quickly draw this. It's a really weird looking mechanism, but essentially, what we've got here is that this double bond kind of transfers over to here. So what happens is this line here essentially becomes one sec. Technical difficulties. There we go. Essentially becomes this. There we go. Essentially, that carbon becomes that line there. And to make this, well, you also need to make a full ring. So what happens is we're going to have an arrow going out. I'm going to have to make another page. This is being really buggy. An arrow going out, and also this bond is going to transfer over to there. So your final mechanism essentially looks like this. It's a really weird one, to be honest. It's a really weird one, but you can still figure out the next parts, I think, without the mechanism. So this one would go there, this one would go there, this one would go there. Does that make sense? So like bonds, essentially, that you can think of it as the bonds just changing. It is a weird mechanism, though. Okay, and essentially you're kind of using this base structure here. You know that any sort of double bond that you have here turns into this hexane, or well, cyclohexene. So how does that interact with this? As long as you understand color arrows. Yeah, 100% actually, yeah. I think the mechanism are really good, rather than they're not. I think the way that teachers teach them is memorize it. It's really about the key thing is understanding. Phone's vibrating, but I don't know where it is. Found it. I keep getting notifications from Temu. They said apparently they're gonna give me £46.13. You know what they tried to do? Yeah, they told me they're gonna give me £170, and then they made me spend £10, and then I never got the £170. Fucking scammers, bro. To be fair, there was some gym stuff, but like still, scam me, £10, free delivery though. Alright, for the question 2, you seen it? What you seen? Alright, question 2. Honestly, acts a very, very similar way. Yeah, listen. I was trying it, bro. I was planning on getting something from Team anyways. That's not the point, bro. That's not the point of falling for it. I was experimenting, bro. If they were giving me a good deal, then fairs, bro. But I was gonna buy it anyways. That's a 4, man. Okay. We have a double bond here, and this kind of makes a cyclohexene with this kind of bond on the left-hand side. So essentially what happens is that you're going to make a cyclohexene kind of ring here as well, which you're going to have that. But then essentially the rest of the structure copies over like so. Okay, that should be your final mechanism or final product. Oh, I got some gym stuff though. I got like wait. Let me show you what I got. They don't fit my face very well though. Try the second one in it, but that. These are cold, bro. These are actually cold. These are actually cold, man. So I got these glasses. Yeah, Team Hall, man. I got these glasses, and then I got just a bit of. I just seen this. I was like, yo, let me try it. This is actually the worst thing in the world. This is actually so pointless, guys. If you go gym, yeah, get your forearms actually working out. Not this bullshit, bro. This is ass. Don't use that. Okay. And then I got like. To be fair, the rest is kind of ass to be fair as well, man. Yeah, man. Come on. Let me put this on. Cold. Yeah, I don't use wrist straps. I'm gonna be real. Train your forearms like a man. Okay, anyways, next part. I'm actually gonna continue this part here using the mechanism way that we did before. Because this is a triple bond, and essentially what we have here is a triple bond and 2 carbon stuff going out like that. What I'm gonna do is make this bond go to there. This bond is gonna go to there. This bond's gonna go to there. But what do I have left over? Well, essentially what I've left over is again a ring. Like so. And then these are going out, and that's a single bond in there, or double bond I should say, and we should have that as well. That works, or if you decide to put that double bond on the inside, that also works. Okay, either is fine. Okay, and that should be a final molecule. Does that make sense, guys? If there's any questions, just definitely ask. I can't lie. No, I'm gonna say no. I'm gonna be real. Like it's if you do the harder stuff, yeah, then it's easier to do the easier stuff. Yeah. I was right, man. Okay. Where were we at? Not mechanisms. Multiple choice. Let's do some multiple choice questions. Okay. The way you should do multiple choice is looking at in terms of what you can eliminate. Okay, process of elimination. Okay, let's look at this. Which statement is correct about group 1 elements? So if you already know, great. If you don't know, we'll figure it out. The first thing you should do is go into the periodic table. I'm going to pull up your group 1 elements real quick. And your group 1 elements are... 1 second, let me bring a screenshot over. These are your group 1 elements. Lithium, sodium, potassium, rubidium, cesium, and francium. The cesium plus ion has a more negative enthalpy of hydration than the rubidium ion. Okay, I'm going to say that as maybe. Maybe. The enthalpy of atomization for potassium is greater than the enthalpy of atomization for sodium. Okay, so you're telling me from potassium gas to potassium to, sorry, that's the other way around. Potassium solid to potassium gas. You're telling me that it has a higher, more positive enthalpy than sodium. What do you think about that, guys? Do you think that is viable? Is that one viable? Okay, you're saying D. Okay. Okay, I like that, Gem. Why have you said D? Because, you know what? You are right with D, actually. You are right. The way you should go about this is, read each one. Think about, is there a lot of work I have to do to go ahead and figure this out? You can say maybe unknown. Maybe unknown. The melting of potassium is higher than the melting point of sodium. Well, is it? It is not. Therefore, the only one that's left over, well, so the second ionization energy of rubidium is lower than the second ionization of lithium. Well, rubidium is back here. Rubidium, if we go ahead and ionize this, at the moment I should probably get the whole periodic table up. Why this straight line plus skeleton should be bent? Let me get the whole periodic table, 1 sec. But the correct answer is 100% D. It's to do with your ionization energies. So let's look at this. Rubidium goes back here, goes to krypton, then goes to bromine. Okay, so at the moment you have 1, 2, 3, 4. So this is a 4s1. Okay, and it has a 3D shells as well. So it goes to 4s1 or 4s0 3d5. Whereas the ionization of lithium goes to well, it actually goes to 1s1. Oh, sorry, this is 2s1, 2p6. This should be a p shell actually. Sorry, it should be 3p5. It's going to be 2p. 2p. Am I tripping? 1s1, 2s1. Sorry, this is 1s2. I'm tripping, guys. Give me a sec. Give me a second. Let me clear my mind. 1 second. 1 second. 1 second. 1 second. 1s1, 1s2, 2s2, 1, 2, 3, 4, 4s. This is a 2s1 actually. 4s1. And then because it's a second ionization energy, 4s1 goes to krypton, then bromine, and bromine hence 4s0, 3p6. Whereas second ionization energy of lithium goes from 1s2 to 1s1. Okay, so essentially what we're checking is the reason why your rubidium has a lower second ionization energy than lithium is because it's just S shell. The closer you get towards your nucleus, your ionization energy ends up increasing. To be fair, I think I did a bit too much work there. I'm going to be honest. I did a bit too much. But a lot of your multiple choice questions are going to take long. Okay, so be ready for that. And be ready to skip. Do not spend longer than, I can't lie, 1 minute 30 and move on. And actually, I think that might be even a bit too long. I'm going to give you 45 seconds. 45 seconds per multiple choice question. If you don't know, move on. Oh, I'm going to give you 1 minute, actually, 1 minute. Look through, you're going to have to work through the process of elimination. Okay, if you know the question, great. But if you're spending more than 45 seconds figuring out what each sentence means, move on. Does that make sense? Yeah. No, that was a quick one. My bad, Mikhail, bro. My bad. Alright. Let's look at this one. Which polymer is not hydrolyzed when heated at aqueous alkali? Okay. The key thing about this one, yeah, is really just thinking about, well, what type of polymers do we have? Kevlar, well, these are essentially, I would say, four. My bad. We have different. Okay, you said C. Okay. It is C. Lock it up, bro. Lock it. It is C. Okay. The reason being, Kevlar, nylon 66, and terylene, they're all condensation polymers. So you need to know this. Okay. Whereas polypropylene is an addition polymer, and the only one that cannot be hydrolyzed, what keyword here is hydrolyzed, is, well, addition polymers. Actually, I take that back. Hydrolyzed with aqueous alkali, anyways. Okay, here you can use alkali hydrolysis. Okay, technically you can use hydrolysis with HCl here, technically, but that requires a lot of energy. Okay, so yeah, cool. Let's move on. This one's a pretty easy one, I'd say. This one's pretty easy. I'm gonna go back to the 2021 paper earlier because I had a bunch of multiple choice questions in there. Okay, I'm going to put a couple on screen, and you guys are just gonna answer them. Okay, if you're unsure, then we'll go through them. Okay, give me like 3 letters. Okay, give me 3 letters. One for the first, second, third. Give me 3 letters, and then do that. If you're unsure, put C. All right, we got CCC. If you're unsure, yeah, what is aqueous alkali? It just means like sodium hydroxide or something. ACD, DCD, DCB, DCD, ACD, ACD. Okay, first one is going to be A. Reason being, questions asking which forms a buffer solution. Buffer solution can only be made with weak acids and its salt, or weak bases and its salts. You do not look at weak bases in AQA or even OCR or even, I don't know about Excel to be fair, but you can make a base with a buffer with weak base and a salt. Okay, it's A. First one's A. Second one is going to be B. Okay, no, it's not. It's not B. It's C. I don't know why I said B. It's C. Catalytic cracking of alkanes. You're going to be using zeolite. Okay, if you want to get that term down. Contact process. You're going to be using V2O4, which is again a solid. Okay, and your sulfur dioxide is your gas. Here, alkanes. They are usually they're going to be gases as well because these are alkenes. Okay, alkene. Sorry. No, yeah, alkanes. Sorry, alkanes. They're going to be gases. Okay, because they're going to be coming from your the thing. What's it called? What's that thing called? Anyways, Haber process, going to be using Fe2 plus, and then C is going to be Cl radical, which is a different state. Okay, last one is going to be D. Why? It's just you just need to know it. Okay, we did it in terms of DNA. The only ones that come off is Cls, specifically because their bonds are weaker. And you can argue the technique is because the bonds are weaker, they are more reactive. All right, let's go to 2022 multiple choice questions. Okay, let's start with the first ones. Let's do these. Yeah, of course, Ibrahim. You're gonna need to make a buffer. You need a weak acid and its salts. So specifically, you know, for example, if you have ethanoic acid, you're gonna need an let's say sodium ethanoate. Okay, that's your weak acid and its salt. And then, for example, weak base, for example, ammonia, and you also need a salt. So, for example, ammonium chloride. Okay, that's what the definition of a buffer is. You guys done that very quick, bro. You guys have done that very quick. 1 second. Good. It is going to be CC. Okay, I'm not going to go over that too much. If the guys have done it, I'll give you guys 1 more minute, but it's going to be CC. We're going to finish this whole paper one. CC, bro. CC. Calm. All right, next 3. Actually, wait. I'll move it up 1 sec. You guys can do 6 at the same time. If you want to give me 6, you can. If you're going to give me the first 3, that's also fine. Or if you want to do 8, 9, 10, and just put it in chat, that also works. Okay. All right. This will just give a bit of time for the guys If you want to write down like question 8 is equal to C or question 9 is equal to blah blah blah, that also works. The C method works. Maybe, man. Maybe. Yeah, what if they make all the questions the exact same answer? So like what if they're all A? That'd be crazy, you know. Okay, you got the 8C. Yep. Why? I'll explain. Graphite has its hexagonal rings. 1, 2, 3, 4, 5, 6. Okay, essentially has electrons in between the different sliding rings coming from your carbons. Methylbenzene, well, because it's a benzene, you have a delocalized electron ring in the middle, so it cannot be B. Okay, sodium is a metal. Okay, you have delocalized electrons surrounded by positive ions. Okay, C of delocalized electrons. Okay, first one has to be C. Okay, the next one is definitely not C. Okay, consider the charge change that occurs in the shape of the curve for the distribution of molecular gases. Okay, I would probably go ahead and draw the graph for this. Let me move this to the side a bit. This is going to be your Boltzmann's graph. But just by reading from this, actually, if it's a higher temperature, can't be more molecules. It can't be more molecules with the mean energy. That's it's a tricky one. But it's not going to be B. Are there more molecules with the most probable energy? Again, there are not more molecules. Can't be more molecules because the same amount of molecules. So the only one there's going to be is D. Question 10. Which of the oxidation states is correct? First one cannot be right at all because we have a 0. I'm going to cancel off the ones that can't be. If sodium is plus, hydrogen has to be minus, so it cannot be this one. It's either going to be B or C. Let's check fluorine. Fluorine is -1, -1. Well, then oxygen has to be 2 plus. Or even actually, sorry, I take that back. Oxygen is always 2 minus. I don't know why I did that. Oxygen is always 2 minus. That means fluorine has to be plus. Therefore, question 10 is going to be C. Okay, I don't know why I did that. Your C method might actually work, bro. It might actually work. 11. Which change to hydrogen electrode has no effect on the electrode potential? Well, concentration definitely not. Temperature definitely not. Surface area potentially, or the pressure of the hydrogen. What you guys say for question 11? No, you're saying fluorine is more electronegative? No, G. C is always, because it's group 7, right? Group 7 things can slightly vary. No. Oh, yeah. Huh? Am I tripping? Shit. My fault, boys. It's still C, though. It's still C. My bad, it's still C. Yeah, 8 is C. 8 is C, HM. No, you guys are right. That's my bad, boys. My bad. Yeah. Fluorine's always negative. I don't know. Yeah, my bad. Fluorine's always negative. So therefore that becomes positive. So we're gonna have that. And we can always check with chromium, I guess, as well. But if that's a 2, okay, we have a -14, and what we're left with is a +7, or technically 14. And this obviously is not 0. Therefore, the only one that's left must be fluorine. Fluorine's -1. Sorry, guys. No, you're right. Fluorine is -1. That's my mistake. No, you got it right. That's a really good. This you have metal to halogen to oxygen. I completely agree. Completely agree with them. That's my bad. Question 11. Let's keep on going with question 11. It's either going to be B or C. Why would that contradict? No. Mikhail, because of that, I know why you're saying that. Because the overall charge of chlorine here is 0, this has to have a 0 charge. Is that, you know what I mean? Because the overall charge is 0. But what you can do is just check the other ones anyways. Yeah, you're saving me armor, man. Yo, should we try the C method again? Question 11 is actually C. Crazy. Okay, why is it the pressure of the hydrogen does not matter? It doesn't affect the amount of essentially your reactants. Okay, whereas the surface area can no, that's not a really good diagram, is it? In a beaker, if you have a higher surface area of your electrode, essentially what that means is that you have more area of your ions to become essentially to go ahead and react. So that means that it has to sorry, the pressure says no effect. One sec. No effect on the electrode potential. No, yeah, so surface it doesn't really matter because it's all reacting anyways. Whereas the pressure essentially is you're increasing the concentration of it technically, so it's gonna affect that. My bad, boys. My bad. Language. My bad. If you guys on YouTube, TikTok, come to YouTube, yeah. You know what, let's try it. C and C. You wanna try it, yeah? C and C. Let me check it now, yeah. Question 12. What is correct? Which is the correct statement about this cell? The EMF value. This one's not C, I'm gonna be real, bro. This is not C, man. It's not C. You know, it was working though, it was working. Question 12. It's not C though. Zinc is deposited. Is zinc deposited? Because we have this on the right hand side, what I'm gonna do is work out the actually I'm probably not gonna even work out the EMF. But since this will get flipped over, that means your zinc solid must be on the left hand side. That means it can't be D. The concentration of lead ions increases. It does not because you're using them up because we're keeping the same equation on this. So again, has to be A. 0.13 minus 0.76. Yeah, 0.63. Yeah, it is. If it's not C when you want it to be C, it's not C when you want it. Okay, all right. That's not bad try, man. That's not bad. Let's try it. Let's try for this one, man. Which cannot function as a Bronsted-Lowry acid. So you're saying to me, if I don't know what it is, or if I guess that it's a C, it's not going to be a C. But if I try it and I put C, it's going to be a C. That's what you're saying. Well, okay. Cannot function as a Bronsted-Lowry acid. Cannot be this one because this can donate a H+. Okay. Cannot be this one because this can donate a H+. Cannot be this one because this can also donate a H+. So what do we have left over? Top one, A. This method not good. See, method not good. Yo, it works. It worked for like the first couple of ones, man. We'll try it. We'll try it again, man. We'll try it again. Okay. C. Boom, boom, boom. All right. What is the pH of 0.02 mole per decimeter cubed of this acid? No. It's not gonna get patched, bro. It won't get patched. It won't get patched. Trust me. It's a good method, man. You know what? I'm gonna approve it, bro. It's a good method. I approve. Alright, 2H plus. So we're gonna have essentially a minus log of 0.04, I believe, unless I'm tripping. Yeah. Yeah, boys, I can't lie, UCAT, long day for you, man, if you're doing UCAT, bro. That was my worst summer, man. That was my worst summer, bro. Yeah. Come on. B. It is B. C method might be patched, boys. C method is patched. Nah, I'm not doing mid. Nah. Okay, question 15. Equal volumes of two solutions, each with the same concentration, are mixed together at 29K. Which two solutions, when mixed, form a solution bigger than pH 7? Okay. So bigger than pH 7, we're probably going to be working with in terms of bases. Well, first of all, it can't be this one. Why? Because we have a weak acid and a hydrochloric acid. It just can't. Your hydrochloric acid is going to take over. Again, here we have a salt and an acid. Can't be this. It's going to be very acidic. Okay. Here we have a weak base and weak acid and weak base. Probably going to be around 7. Okay. So it can't be this. What we're left with, B. C method is patched, boys. C method is patched. Come on, Emma. You're doing engineering, nice. Which ionization needs less energy than this process? It's going to be to do with your periodic table. Let me get periodic table up. 1 sec. It's not even on this page. Let me go back to the other page. 1 second. Let me rob it from here. There we go. Which ionization needs less energy than this process? Well, we have Mg, which is here. Can it be Mg plus to Mg2 plus? I'm going to say no, because Mg plus has the same electron configuration as sodium, and that will go to neon, because then we'll go into our full outer shell, so it cannot be this one. Beryllium. Beryllium is a lower energy level, so it has a higher ionization energy, so it cannot be beryllium. Argon. Argon is, you're going from a full outer shell, so it cannot be argon. What we're left with is aluminium. That's a matcha. Matcha, yeah. Maybe, man. Maybe. Let's get a matcha, bro. Let's get boba. Let's get boba, man. Your boba actually banged. Let's be real, bro. Like, I don't understand the hate about boba. Like, it's completely valid to have boba as a guy, man. Question 17. Which statement is correct about the group 1 elements? The cesium ion has a more negative enthalpy, or well, we just did this actually earlier. We did get this D. This is patched, bro. This is patched. 18. Question 18. A test for chloride ions in aqueous solution involves adding dilute acid followed by an aqueous nitric acid. What's the reason for adding nitric acid? To prevent the precipitation of other silver compounds. This is patched, bro. It's actually patched. Boba is valid, bro. What about boba is trash? Boba is literally valid. I can understand why people might not like matcha. Like, I tried matcha. It's kind of ass. I'm a bit real. Which pair of reagents reacts to form a tetrahedral complex? Here I would probably try to make some molecules. First one I'm probably going to try is this FeCl3, because this one's actually potentially one that that it might be. But if I have FeCl3 and I also have chloride ions, this is probably going to make a FeCl4 minus potentially. And let me check with the other stuff. But cobalt chloride and concentrated ammonia. That's probably going to make cobalt. I'm not sure what that would make. I'm going to be honest. This is probably going to make some sort of base and salt. So this is going to make copper, ammonium, copper sulfate, and ammonia. No, copper sulfate is really a salt, and this is a weak base, so I don't think these would actually react. And same with this, to be honest. So I'm actually going to give it to D. Let me double check if it is D. It is D. C method is patched, boys. C method is patched. Don't use the C method. I don't approve. I said I approve before, but I don't approve anymore. Alright. It's just the last, there's like 30, there's 35. So you know what, finish off these multiple choice questions and then that'll be the end of it. Cobalt chloride solution changes occur when excess. Actually, you know what, I'll give you guys this page. Try it. Let me know what the letters are, and we'll go through anything. Kebab voted for results day. Say no. Wait, on me, on me. I was gonna say no more, but it's on me, man. B. You're saying B? It is B. I do agree. I do agree with that. Because ligand substitution, all your transition metal stuff, or a lot of transition metal stuff, will be ligand substitution. Cool. 21. You're saying B or C. What volume in decimeters cubed? So this is just kind of a reaction that you're doing. If you guys want to give all the letters in 3 ways, I mean in 3 letters in 1 message, then just do that. And to be honest, I'm looking at time as well, 9, 10. You know, we'll do these 2 pages and then finish off. The key thing is though, look through all of the questions, or all of the options that you have in the multiple choice. Don't just do what I was doing earlier, because that's going to waste time. Scan through it, see which it might be, which it might be, and which it might not be. If it's not, confirm the fact that, okay, why is it not? If it's a question mark, then cancel off the ones that you do know 100%, or yeah, cancel off the ones or tick the ones that you know 100%, and then give a guess. Okay, you're better off, okay, cancelling out maybe 2, and then it's a 50-50 chance. Okay, if you're really unsure, and do that in terms of time as well. Okay, if you're 100% sure that it's not A and maybe it's B, C, D, in this case, I think you should do, in terms of calculation questions, you should work it out. But for example, if it's B, C, D, then you now have a 33% chance rather than a 25% chance. Yeah, my bad, Mikhail, bro. My bad, man. If hemoglobin's actually see you later, Jacob, man. Take care. If hemoglobin comes up, I'm not gonna be happy, but you should be fine, man. Essentially, the main thing about hemoglobin, you need to know that it bonds to iron with ligand substitution, and if you do biology, then this will probably help you. And there are different groups, specifically your heme groups, that can take on oxygen as ligands, essentially. That's more or less everything you know about hemoglobin. It's more, to be honest, you look at more about hemoglobin in OCR than AQA. I've never ever seen it in AQA, I'm going to be real. Ever. I wouldn't even learn, like, when I was learning, I did not learn anything about hemoglobin, really. I think it was like a 10-minute thing. But hemoglobin bonds is ligand, it binds it with ligand substitution, or just even, I should say, dative covalent bonds, I should probably say. And if there's any different sort of groups in your hemoglobin, specifically your heme groups, and you want to bind anything, you're going to be binding them with ligand substitution and with oxygen. Okay, you don't want carbon monoxide, because your carbon monoxide has stronger bonds to your heme. And what happens is, if you have carbon monoxide in your blood rather than your oxygen, you die. Yeah. Yeah, carbon monoxide poisoning. Yeah, Fe2 plus. Yeah, it is Fe2 plus. Yeah, good question, BMT. It is in your formula book, kind of. Like, you have the structure of it. You might be able to figure some stuff out. But yeah, let's quickly go over this 21 and 22, and we'll finish off here. What volume in dm cubed of 0.02 moles do we have? I would probably just rewrite this below, actually. I'm going to write it here. 5V4 plus MnO4. Okay, and then we have moles, concentration, volume. I have 0.02 moles of this. I have 0.1 moles of this. Oh, sorry, that should be 0.02 moles per centimeter cubed there. What's asking is, what is the volume? So I need to work out what this moles would be. So I'm going to divide through by 5. So that gives me 0.02 moles. So that means the volume here, if N is equal to concentration times volume, and my volume will be moles divided by concentration. Therefore, my volume will have to be 1. Therefore, your answer is C. C method might be back, bro. Okay. 2-bromopropane reacts with bromine to form 2,2-dibromopropane. If you ever have this, and I heard that this was in paper 1, I mean paper 1? Maybe paper 2. There was free radical substitution in one of the papers, and if you came to the lesson, I did mention, if you have some sort of haloalkane and you're trying to convert it with into another haloalkane, you have to use free radical substitution. Who used it? Please tell me you guys used it, because when it came up, a lot of people were not happy about that. Okay, if you're trying to add on a halogen onto an any sort of alkane, it has to be through free radical substitution. Nice, Ibrahim. Nice. Okay. Alright, guys. We're going to finish off here. Well done. And smash tomorrow's paper. Let me know how that goes. I know you guys are probably in the Discord. So, yeah. I'll see you then. Enjoy. And live life. You put nuclear edition. Should be... It's alright. It's alright. But it's going to be... Oh, bro, thanks, man. I appreciate the donation, man. Thank you very much. Oh yeah, my prediction. Yes, on you. Let me make my predictions real quick. Yep. Let me make some predictions real quick. Okay, so before we finish off, quick prediction. Iodine clock test, 100% popping up. Okay, chromatography in some way. I don't think it's gonna be TLC, but there's still a chance it can be TLC. But realistically, I think it's either gonna be your column or your gas. I've barely seen it. Oh, I'm gonna say even I've never seen it in one of the past papers. Okay, revise your specific heat capacity in depth, meaning not necessarily your Q equals MC delta T. This is the easy bit. Okay, specifically the graphing for it, because the way that the graph for specific heat capacity works is that at first you measure the time. Okay, so this is kind of like your temperature, because you're kind of measuring your temperature, and what happens is suddenly it drops. Okay, and actually it kind of looks something like this. And what happens is you need to work out, or you have to kind of draw a vertical line between this and this. Okay, if you know what I'm talking about, if you did the practical. But yeah, that might pop up, that could pop up. But these are the big two. On top of this, DNA drawing. Okay, DNA drawing. Be confident with this. Be confident with your base drawings. Okay, Zeta ions. I think they're popping up. Multiple choice in some way or form. Okay, they came up in 2024. A lot of people got them. I don't think many people are actually confident with them. It's considered an easy topic, but most people brush them off. Okay, reason being, when you make these potentially, yeah, maybe. 1 second, let me find the formula book. Stay with me. Stay with me 1 sec. I just want to show you this real quick. Here we go. Okay, so when you have these amino acids, right? And I thought I actually got this question right, and I didn't get this question right. But essentially, the key thing about zeta ions is that overall charge is 0. You need to remember this. Okay, this will help you work out your zeta ions for everything. Okay, your zeta ions for your alanine will turn into a minus and a H3 for NH3 plus. Okay, it does not do it for everything though. So for example, for aspartic acid, it only does it for the top bit. I did mention this in my paper 2 revision session. Okay, it only does it for the top bit. For the bottom bit, you just leave it alone. Okay, you want to make sure the overall charge is 0. In comparison though, if you do have low pH, and you guys probably do know this, low pH means more H plus ions, so this turns into a NH3. Okay, and if you do have any sort of side chain with NH3, that should also turn into NH3. Does that make sense? Okay, and same thing for high pH, which is more basic conditions. Both of your chains will turn into C double O minus. Only in a zeta ion is you're going to do the top, only the top bit for zeta ions. Okay, let me just check what chat is saying because I can't see chat. There we go. Okay, KCKP, I think it's popping up in some way or form. There will be one question on it, at least a big one. What else is there going to be? Rates, I don't think it's going to come up like that. I don't think rates coming up. I'm going to be real. There might be a table multiple choice. There might be like A, B, C, D, fill in table, which is the correct number. It's going to pop up in that. In terms of inorganic prediction, good questions. I do think there might be some sort of more transition metals, specifically equations. Okay, specifically equations on aluminium 3+ or your Fe3+. These are the hard equations, and they can pop up in your multiple choice. Watch back my paper 1 revision session. Okay, on my channel, I go over this in transition metals. We go everything. So I've marked out the time. It's really easy. You can just check in the description. There's like a timestamp for every kind of topic. So I sorted that out because someone asked me in my Discord. I can't remember who. So I sorted that out. So watch that. Okay, transition metals. I think they're gonna pop up again. Okay, E equals HV potentially. I think it's like I'm gonna give it a 20% chance. Just because it didn't pop up in paper 1, and And in paper 1, in the 6 marker, it also talked about the wavelength of light in the mark scheme. I've seen it in the official mark scheme. So wavelength of light in some way or form. So I'm going to give it a 20% or maybe even a 10% of it popping up. So I don't think it's going to pop up. It came up last year, then fair. These are my main predictions. These are honestly my main predictions. For inorganic, also period 3, I'm actually going to add period 3. This period 3. This comes under transition metals, Archie. Watch back my paper 1 video. Okay, but there will be some sort of equation. I think there will be an equation one. Okay, these are my main predictions. Yeah. Good luck, guys. Smash tomorrow's exam. Period 3 comes up. I think it might. I feel like it could do. I've heard that it was quite small in paper 1. 1 second. Let me move these up. You guys kind of have a nice screenshot. Okay, these are some predictions, anyways. Obviously, take these with a grain of salt. But yeah. Yeah. Bring exactly the Planck's constant. Yeah, it is. Okay. Really appreciate it, Raheem, man. You guys have been cooking. Honestly, you guys coming is your own revision. Not everyone does this. Like, I'm not a big channel or anything, but yeah. Good luck. Let me know how it goes. Comment in the Discord. I'll go TikTok live anyways after. I'm thinking probably tomorrow I'll go TikTok live. I'll see how you guys are doing. But yeah, smash it. Appreciate it, guys. I'll see you guys later. Take care. Mel, I did in paper 1. I did. So go on my YouTube. Yeah, go on my paper 1 video. Just watch that back. Okay. Alright, I'll see you guys later. Yeah.